Get started in a minute. For those of you in the program who haven't seen this yet, I've printed out a prototype of the intern book. This is all the work that you've done this summer. So that will be actually getting bound, and students and advisors will get a copy. All right, so
are you going to do the lights?
I will do the lights in a minute. There's these flyers on the chair at the back that give the program for today. And there's food which you should consume. So with that, if we're ready to go, are we live? Then welcome to the 31st. Oh, I'm old. The 31st SAO Astro REU Student Symposium. So we had 9 students this year from across the United States, from California to Puerto Rico to Edinburgh and Shanghai. You may not have known those are part of the United States. And our students have been working so hard this summer. I'm so proud of what you have all achieved. And we're going to hear today about asteroids, about stars, about galaxies, about clusters of galaxies, the whole range of astrophysics from the near to the far. And so today's proceedings are organized sort of in that order, from stuff near to the Earth to the very distant stuff. We will have 3 talks in the first session. Each talk is 12 minutes plus 3 for questions. I will raise my hand when you have 1 minute left to go. And then after the first 3 talks, there will be a short break. We have another 3 talks, and then the lunch break, and then the final 3 talks in the afternoon. So, without further ado, I've got a couple minutes to stall because I said we start at 10:05.
Jonathan, do you know how this works?
Yeah.
I just
You kind of clip it to yourself, and then you need a pocket. So you might want to use the. Yeah. You don't want it to be too close to your mouth. So let's see. Why don't you test and see if the mic is on?
Testing. Testing.
Yeah, that sounds good.
Okay,
Awesome.
good. So should I go ahead or?
I'll introduce you in just 1 second. I think we're ready to go. So, our first talk today is by Ivaris Martinez Seirano from the University of Puerto Rico, Martinez. And Ivaris has been working with Stephanie Jarmak on asteroids and on JWST data. How cool is that? So I'd like to turn the floor over to Ivaris for our very first talk. Go ahead.
Okay, so hello everybody. My name is Ivaris Martinez Seirano. I am from the University of Puerto Rico, Mayagüez. And today I will be presenting a little bit about the work I did throughout the summer with my advisor, my mentor, Dr. Stephanie Jarmak, which concentrated on the surface composition and hydration of 2 asteroids, 16 Psyched and 225 Henrietta. First, I would like to give you a general overview of what I will be presenting throughout this talk. And I'm sorry, I'm like super nervous. I'm like, okay, so first I will try to go through why it is that we study asteroids and their hydration, specifically why we're looking at 16 Psyched and 225 Henrietta. Then I will try to explain a little bit about how it is that we go about detecting this hydration on their surface. And then I will try to present a little bit about what my advisor found on the hydration indicators on Psyched. Then I will derail the presentation a little bit to talk to present a possible method for distinguishing between endogenous and exogenous hydration. And then at the end, I will try to present the hydration indicators the preliminary results that we have on the hydration indicators on 225 Henrietta. Okay, so first off, why are we studying asteroids? So it turns out that asteroids are considered to be primordial remnants from the early solar system. And they are thought to have gone through fewer collisions, meaning they have gone through relatively small changes. Also, their smaller sizes make it so they go through less internal changes and in comparison to, for example, a planet. Studying them and then they help us understand the materials and processes involved in planet formation. This is because their composition depends on where they were formed in the solar nebula. This is a really cool diagram that shows the temperature of the sun versus the distance from the sun. And at the 4.5 AU mark, right over here, there is what we call the frost line, also otherwise known as the snow line. And asteroid composition depends on where they formed in this snow line. This is because asteroids that form over here are expected to have a more dry composition because the temperature from the sun evaporates the water. If an asteroid were to be formed in this part of the solar system, we would expect it to have more hydrated composition because the sun, the temperature from the sun is not as high and therefore it does not evaporate the water. This means that if we find an asteroid that is hydrated in this area over here, something must have happened for it to move to that area. Okay, and so I'm going to explain a little bit about our asteroids. One of our asteroids of interest is 16 Psyche, which is found in the main asteroid belt, somewhere right there, over in the middle of it. And this asteroid was discovered by Aníbal de Gasparis, an Italian astronomer, in 1852. And it is characterized as an M-type asteroid, meaning it is considered to be made mostly out of iron and nickel, similar to Earth's core. If Psyche were to be a perfect sphere, it would have a diameter of around 226 kilometers or 140 miles, which would be comparable to the state of Massachusetts, leaving out Cape Cod. Psyche's size and composition make it so that one of the leading theories about its origin is that it is the exposed core of a protoplanet. And this was so interesting to a bunch of asteroids that NASA actually created a mission which they launched in October 2023 and is estimated to arrive at Psyche in August 2029 to study it further. The other asteroid that we are interested in is 225 Henrietta, which is located in the outer main asteroid belt, somewhere over here. It was discovered by Johann Palisa, hopefully I'm saying that right, an Austrian astronomer in 1882. And it was characterized as an F-type asteroid, which falls into the much broader range of C-type asteroids, which means that it is made mostly out of carbonaceous material. Henrietta's length is about 128 kilometers, or around 79.5 miles, which is comparable to the size of the Delaware. Okay, so how do we go about detecting hydration in these asteroids? One of the things that we like to do a lot is do spectral analysis. This is where you take the asteroid's reflective intensity and you compare it to the wavelength, and when you do this, you get something we call a spectra, which looks something like this. And here you can see this, I don't know if I'm saying it right, but I call them mountains, like mountains and valleys, which we call spectral features. And it turns out that each material has unique spectral features that can be compared to the spectral features found on asteroids to better understand what's going on their surface. There are two of these spectral features that we look for when we are studying the hydration of asteroids. The first one and the most used one is the 3-micron absorption feature, which is caused by the oxygen-hydrogen bond and is indicative of hydroxyl and or water, meaning that if we were to detect this on an asteroid, we would be detecting hydrated minerals. There's another feature, which is the 6-micron emission feature, which is caused by the hydrogen-oxygen-hydrogen bond, and this one is just indicative of water. My advisor's team set out to characterize these two features on the surface of Psyche using JWST data. And throughout the summer, I focused on the 3-micron feature, but if you are interested in knowing more about the 6-micron feature and what they found, I encourage you to go to her paper where she goes into much more depth about what I'm saying. Okay, so they found that Psyche has a 3-micron feature with a depth of around 4.3 to 6%, meaning that hydrated minerals were detected on the surface of Psyche. And this is where I would go on to present the preliminary results of Henrietta, but I want to derail the presentation a little bit to answer another question that is really important to asteroid scientists. This question is of whether the hydration on an asteroid comes from exogenous or endogenous sources. This is really important because exogenous sources suggest collisions between asteroids, and endogenous sources suggest formation beyond the snowline. So exogenous means it comes from outside, endogenous means it comes from inside. One way in which we can try to figure this out is by investigating the precise location of the water-bearing minerals on the surface of the asteroid. So for example, here I have a slice of Psyche's data, and if we were to find that there is water-bearing minerals all across those pixels, we would say that this would be more indicative of an endogenous source, meaning that it most likely formed beyond the snowline and then later moved on to where it is now. And in contrast, if we were to find the hydrated minerals to be in a really concentrated spot not a specific place, but just in a specific concentrated spot, this would be more indicative of an exogenous source, because this would mean that an asteroid might have impacted Psyche in that area and then have left remains of hydrated material. When we tried to do this, we found that Psyche, the spectra actually has what we called wiggles. These are sinusoidal noise that comes from JWST's point spread function. And what the point spread function does is that it takes data from a single point and then it spreads it out over, in this case, a 1 arcsecond aperture. So if you integrate all the spectral data in a big aperture, like you see at the top, there's enough signal to noise ratio so that the wiggles disappear. But if you try to go to the spaxel level, you can see all of this noise. And if you want to study asteroid surface further, you need to find some way to get rid of this. Thankfully, there was another team that found that they had the same problem, and they created a code that uses this function over here to model these wiggles out. And we tried this. We modified the code a little bit to fit our data, but we found that it mostly got rid of the wiggles. And even though this approach would not work on the data we have of Psyche because it is unresolved, this approach could be applied to other asteroids in the future. So going back to Henrietta, we integrated its spectra over a large aperture, so we didn't have to worry about the wiggles. And this is the flux that we got. Then we subtracted the solar flux, and this gave us this normalized reflectance. And as you can see here, there is something like some feature that can be observed in the 3 micron region. And after playing around with the data and making it pretty, we created a relative normalized reflectance graph, which allows us to then better characterize that 3 micron feature. And we found that it has a band center at 299 microns and a band depth of around 8%. When you compare this to Psyche, there isn't really much of a difference. Its band center has a difference of 0.02 microns, and its band depths have a difference of only 2%. This comparison reveals that both asteroids exhibit relatively similar features, around 3 microns. Future steps would be to compare Henrietta spectra to laboratory spectroscopic measurements, sorry, that word is hard, of carbonaceous chondrites, as my advisor did on her paper for Psyche, and also study other asteroids like 142 Polana, which JWST's Go program ID 3760 is planning on doing. So if you want to check that out at some point. And that would be all. I want to give a special thanks to Stephanie Jarmak, my advisor. I would like to thank Jonathan for being such an amazing director. I would like to thank also Matt Ashby for giving us feedback on everything, and JWST's Go program ID 3760, which gave me the data that I needed to present today. Oh, and also my amazing cohort, I love them so much, which they made this program that much better. And my family, which probably are seeing this from YouTube, hi. And yeah, with that all said, do you have any questions?
Thank you very much, Ivaris. Questions for Ivaris?
No.
Martin and then...
You talked about where the bandwidth was centered in 0.02 or something, but the width itself is pretty large and noisy. I wondered how accurate it was determined. What's the uncertainty on the band center?
I am not quite sure. I think we would have to, wait, where is it again? This one. Yeah. I think going about what my advisor has done on her paper, we try to fit different Gaussians for different band centers, and then this gives us a better idea of what it would be going on the surface of Psyche. So because we did this kind of rush, we only could do it for one band center, but for a paper we would do it for like a multiple band centers and create like it's not a region, but more like different values of what could be going on Psyche, if that makes sense.
You have here 2.99 plus or minus 0.01 roughly on there. So that 0.01 is the statistical error in the fit.
Okay.
Right, I think so. So that gives you like some measure of the accuracy, but it's
Thank you.
statistics as well.
Thank you, that's helpful.
Matt, you have a question?
Yes, thank you for an excellent talk.
Thank you.
I guess I have a couple comments. That was the first one. The second one is that there's another mission besides Psyche that this is relevant to, and that would be Sphere X,
Yeah.
which hasn't launched yet, and it's going to launch at the end of February. So it's all built. It's gone through most of its testing, and it's just awaiting installation on the rocket now. And among other things, it's going to do an all-sky spectroscopic survey. So it's going to get spectra of everything in the solar system, all the asteroids, and it will return thousands of spectra at 3 microns for asteroids, carbonaceous, metallic, all those things. So if you're still interested, you could apply this terrific analysis to those sorts of things in a couple of years when those data all hit the archive.
Yeah. Thank you so much for mentioning that. I forgot to mention the sphere expansion. Yeah, that's true.
Andrea.
Are there other ways of detecting signatures of hydration? And can you tell us from the beginning what's hydration exactly? And then can you see it? For instance, can you detect a in the radio region, a water molecule from these things? I mean, is this the only way?
I think I would have to do more research on that. To answer your question on the what exactly is hydration, let me go back to here. Okay, so we classify as hydration any type of mineral that has hydrogen or oxygen bond in it. So, for example, like water, H2O has 2 hydrogens, 1 oxygen, that's water. But there are also other minerals that have hydroxyl in it, and hydroxyl could be also, we use hydroxyl as an indication of hydration on the surface of an asteroid. I'm not sure if we would be able to detect this in the radio. I have only heard about the 3 micron, the 6 micron feature in the infrared. But I'm not sure actually. I will have to look more into that. Thank you for mentioning that.
Okay,
Yeah.
thanks.
I have one last question. This is kind of silly, but what's your favorite asteroid and why?
I guess that's a difficult question.
No!
I guess I would have to say it's between these 2, Psyche, because it's the one I worked on most. But I guess we still don't know much about Henrietta. It could become my favorite asteroid at some point. But yeah, thank you for that question.
The right answer is 4589. We have time if anyone has any more questions. Yes.
What does the band depth tell you about the hydration characteristics?
It's basically so it basically tells you about the strength of that detection. So if you had a really deep band depth, it would be you detected this feature minerals. The thing that you're looking for, if it has a really big band depth, it means that you detected it really well. If it has a really small band depth, this means that you maybe need to reconsider if you actually found it or not. So basically, the deeper it goes, the better detection you made, basically.
Maybe I missed it. Why do they vary? The depth between, is that because it rotates or something, or?
On the observations?
There are 2 observations.
Yeah, for Psyche.
And the band depth varies.
Mm-hmm. These were 2 different observations. So yeah, the data would be different for the 2 observations. I guess you could say that it was because Psyche rotated, but I'm not sure if it could be applied just to that. Just because I know that when we do this fitting on other band depths, other band centers, the band depth changes. So to answer your question, Psyche is rotating, and it is we're seeing a different area, but I don't think it would affect that much because I didn't explain it in this presentation, but the way Psyche is rotating means that we are mostly looking at its north pole. So if it rotated, we would kind of be looking at the same thing. So I guess it's just a matter of the data that NIRSPEC captured, but we would be seeing kind of the same area of Psyche. Yeah.
All right. Well, thank you very much. Let's thank Ivaris. So next we're going to get Julie Sage. Julie, Abby, do you have Julie's?
Yes.
Well, maybe we can try. Do you think you can present it?
Do you have it on PowerPoint? I have it on Google Slides. Okay. Does it still have the speaker notes? No. Well, that's a problem. How did you? Oh wait, no, it has. No, it does. Okay.
Oh yeah, you're probably so much better at this than I am. You're a kid.
Yep. I am very well aware with these mics.
Let me see if I can get the speaker notes for you with my. Outside of the solar system, but not so far outside, just to nearby stars. So Julie Sage is no stranger to the CFA. She is at the University of Massachusetts Lowell, but has been a regular attendee here in Phillips of open nights since you were how old, Julie?
12.
12. So it's really nice to be able to introduce her as the speaker in Phillips for the first time. Julie has been working this summer with Paul Cristofari. And Andrew Dupree on estimating surface magnetic fields and atmospheric parameters of stars using spectra from the WINERED instrument. Yeah, take it away, Julie.
All right. Well, title slide has already been given, so we're just going to hop right into it. So, is the stellar structure. So in Size-Linewidth stars, it's layered almost kind of like an onion. So after the core, there is something called the radiative layer. And that brings the heat from the core to the next layer through the process of radiation. Then after that is the convection zone, which basically is where the plasma, it moves hot plasma to the surface, and then when it cools down, it moves back down and creates convection currents. Then there is the photosphere and chromosphere. Due to the rotation of the star, there are those layers can actually experience shear forces. So there's a whole lot of movement going on within the star. The movement of the particles within these layers can lead to the generation of magnetic fields, which is referred to as the dynamo effect. In dynamo models used to explain magnetic fields, there's something called the tachocline, which is the line between the radiative layer and the convection zone. And that plays an important role in these models. The thing that's interesting, and one reason why small M dwarfs have become of interest, is because they can become so small that they don't have a radiative layer, and thus don't have a tachocline. So there has to be different dynamical processes than what's in the models that doesn't depend on the tachocline. So one way that is used to be able to observe these stars and try to figure out what's kind of going on is spectra. But the thing is, the spectra doesn't look like the spectra you may typically picture of like the color gradient with your black absorption lines. These absorption lines come from elements and molecules in the photosphere of the star, and we instead see the spectra as a plotted curve, where the x-axis is still wavelength, but instead the y-axis is something called normalized flux, which is the percentage of photons we receive at that wavelength, when there is no absorption, it is at a 1, and then it decreases into the decimals from there as there is more absorption, and thus absorption lines appear as dips in this curve, as you can kind of see here. And the darker the line, the deeper the core, which is the center. And then the wings, are basically where that line fades back out. And so with the spectra, to be able to analyze this spectra, we need to use something called synthetic spectra, which this is an example from another paper, Tabanero 2018. And so synthetic spectra is computed spectra of what that spectra would look like if a star had a certain set of atmospheric parameters like effective temperature, surface gravity, and metallicity. To make the synthetic spectra, what happens is we make a model of the photosphere, and then we use what we know about the physics of how light moves through the photosphere to be able to make the spectra. And so, as I said, this picture is from Tabanero 2018, and this black line, which might not be very super easy to see just because it's a very thin line in this figure, is where the data is, and then the red line is an example of synthetic spectra. And as you can see, they don't match up perfectly, and that is because synthetic spectra is not perfect. It's not perfect because we don't know all of the physics that is happening inside of these stars, and specifically infrared wavelengths can be more difficult. Also, magnetic fields can play a role in this mismatch, and that is because of something called the Zeeman effect. So a direct consequence to spectra being in the presence of magnetic, or a direct thing that happens to spectra is that when in the presence of magnetic fields, there is the Zeeman effect of where the energy levels split, as you can see in this picture here at the top. And that then creates more possible atomic transitions, and thus it splits the atomic and molecular spectra features. As you can kind of see here on the bottom, you have like one big spectral feature, and then it kind of gets split into 3. However, usually when you're looking at the spectra, you do not see that split as you may do in a laboratory. That is because of a combination of factors of instrument resolution and rotation of the star. All of those individually cause those lines to broaden. And eventually, they broaden so much and just gang up on the spectral lines that it just smooths itself out and just appears as one big broadened line. There's also the effect of magnetic intensification, which I'll talk about later on. So, to model these magnetic fields, the synthetic spectra is created a little bit differently. It has to include as well as the magnetic fields on top of the atmospheric parameters. So, these ranges here, with the effective temperature for low temp stars and high temp stars, surface gravity and metallicity, is what we used for stars for this synthetic spectra that we computed using Z-Turbo. And then with the magnetic fields, we computed it a little bit differently than other studies do. So some other studies model a single magnetic field strength, such as like 2 kilogauss, and they find the percentage of that strength. However, we instead make multiple synthetic spectra of 0 to 10 kilogauss in steps of 2, and use linear combinations, such as down here, to find a more accurate value. So basically, what it is that each S is the synthetic spectra of that specific field. So you have the 8 kilogauss synthetic spectra, the 10 kilogauss synthetic spectra, etc. And then these A is what we call the filling factors. That is basically the percentage of that field strength of what we see. And what this allows is to model more complex magnetic fields. This is because for a star, as you can see, there's a whole lot of magnetic stuff going on around on that surface. And so there's not one single magnetic field strength around that star. Instead, the surface can have a bunch of different magnetic field strengths in different spots, and so doing this linear combination can allow to better model that. And so, when doing the study, we used the WINERED instrument. Specifically, it is we used its high-res Y mode, which covers a wavelength of 0.96 to 1.11 micrometers, and has a resolving power of 80,000. Resolving power is just a quick thing of a wavelength over delta wavelength. And the WINERED instrument is installed on the Magellan Clay telescope, which is pictured here on the left. And then this is the actual WINERED instrument, but on a different telescope. So these are the stars that we observed. So we have multiple stars that are M-dwarfs and K-dwarfs, with one being a G-type star. We selected multiple K-dwarfs since they're easier to characterize due to their brightness and can be good to use as kind of like a basis level. There are other interesting traits within the sample as well, such as some of them being young stars. Some of them have veiling to them, where basically there might be like a protoplanetary kind of disk around them or something like that, and that also causes a whole bunch of stuff with the modeling, as well as some variable stars. So here is an example actually of some of the data and of the fitting. So the process that we go through is after all of the synthetic spectra is made, each of the synthetic spectra is compared to the observational spectra on how similar they are to each other. The spectral lines selected to fit are purposely made to be diverse, of where we choose varying shapes of them, varying depths of like shallow lines or really deep lines, as well as different ones with magnetic field effects. So every line does not feel each line feels the magnetic field differently, which is said to be like, it's put out as lambda factors. So some have higher lambda factors, which means they are more affected by magnetic fields. So the lines all interact differently. So it's good to select lines of varying lambda factors to be able to get a good idea of all the different parameters. Another thing is we have to be aware of is tellurics, which are the absorption features from the Earth's atmosphere. Since we're observing with a ground telescope, there is absorption that happens. So there are some lines that kind of have these funky things to them, so we have to take those out because we can't really use them. And then the program we use to compare is called ASAP, and it fits all the synthetic spectra computed from Z-Turbo to the observed data using an MC process. As seen here is a sample from the V1217 SEN spectra. The magnetic model can actually fit the data pretty well. So the fitted model, the magnetic model, is the blue. And then if you see the red, that is the non-magnetic model. This is what I was talking about with magnetic intensification. Basically what happens is it is also due to the Zeeman effect, but it appears as intensification instead of broadening because the lines split so close together that it leads to more probability of absorption in that area, and thus creates like a greater absorption feature basically. But yeah, so this is an example of a couple of spectral lines and how it's really important to have the magnetic field as part of the model, because the non-magnetic model is just very, very different. So when comparing values estimated through our analysis with the values found in previous literature, our values actually agree pretty well. So the x-axis are values found within the literature, and y-axis are the values we estimated. And the black line is if they were in perfect agreement with each other. Effective temperature and V sin I are pretty well in agreement overall. Beneficity appears a bit scattered, but when you take the air bars, I can speak, I swear, into account, it also agrees decently well. And then the surface gravity is more scattered, but it's known that it's kind of hard to constrain surface gravity using spectra, so it's actually not horrible. And then there is a relation that is interesting to investigate, which is a relation between magnetic activity and rotational period. It has been seen in previous studies that they scale together, most likely due to the dynamo effect. It has also been shown that magnetic activity and the average magnetic field are linked, so the average magnetic field can be compared to the rotational period to check this relation. A previous study, Rayner's 2022, is plotted here as the black crosses with a large sample of stars. And the red dots are 8 of the stars we observed at which rotational periods could be found. And it shows that generally the stars follow the relation with the average magnetic fields that we estimated. However, usually this is instead put as, instead of rotational period, as Rossby number. And this is because the Rossby number, you can easier, it's better to see the relation between the Rossby number and the average magnetic field instead of rotational period. So the Rossby number is the rotational period divided by the convective overturn, which is the time it takes for one convective current within the convection layer to make one cycle. And again, we use Rayner's 2022, and the red dots are 5 stars of which K-band magnitudes could be found. And to calculate the Rossby numbers of the stars we observed, we used relations from the papers Wright 2018 and Mann 2019. And it can also be seen with this graph that it actually follows the relation pretty well for the average magnetic fields that we found. So for final conclusion of just kind of like a summary, what the end result of the paper is that we can in fact constrain atmospheric parameters and magnetic fields of sun-like stars, and that tools and methods that were developed before can be used for WINERED as well in systematic investigations. And the magnetic fields that we found follow the relation between the average magnetic field and the Rossby number. And then for next steps to publish, there's still quite a bit of work to do. Got to identify the elements that we used that are associated with the spectral features that we used, finding other spectral features that might be helpful, as well as investigating the differences of the ones that are really far off the edge of going through the literature to figure out kind of what's going on there, analyzing more stars and running more specific tests on the stars that we do have to get more accurate results after investigating what might be causing the differences. And yeah.
Thank you, Julie. Questions for Julie? Jenny?
Awesome talk.
Thank you.
Cool project. I was wondering if the magnetic field tells you anything else about the stars. So you related it to the rotation. Could it tell you about the age or anything else about the stars, like evolution?
It is. I know it's connected to stellar evolution. That's an important part of kind of especially with the modeling. It's all kind of just connected together. So it's not the magnetic field doesn't necessarily tell you about, you can technically use it to tell you the rotation of the star, but there's a lot of other methods that's easier to use to figure out the rotation. So you usually do it the other way of using the rotation to kind of figure out where the magnetic field could be. But yeah, so it's it is important to the evolution of the star.
Can I ask what motivated the sample that you had to kind of look at the stars? Do you know why they were chosen?
So the being able to use the WINERED instrument, you can't use it for a very long time. It's only active for so long. So it's basically you don't really get a choice of where you're able to look. It's basically whatever is in the sky at that time of observation. So it's just kind of picking out stars that would be good. But we chose K dwarfs and M dwarfs because the K dwarfs, like I said, they're easier to characterize. So they're a good basis. And then for the M dwarfs, that's where if they get small, if we happen to pick one of the ones that are small enough that are fully convective, then you can kind of see, does it fit within that relation between the rotation and the average magnetic field? Is it different? What's kind of going on? You can try to figure out, be able to see kind of what's going on. But yeah, most of it was just kind of, oh yay, it's in the sky.
Presumably there's a brightness limit.
Yeah, no, there's the brightness limit of, it has to be bright enough to actually be able to see it. Yeah.
So you were fitting these Zeeman split lines. What particular lines do you happen to know? The particular lines that are important, or is it just a whole bunch of lines?
There's a whole bunch. These.
So these
two,
ones in particular. Do you know what they
these
are?
ones are good. I do not know which elements they are specifically. That's the thing. I have to go through the Bohl database to figure out. But yeah, so we were using these ones. I was using usually as an example. It also kind of depends on the star itself.
But typically you're using 2 or 3 lines rather than a whole, like 50 or something?
Oh no, it was a lot. I was running 30 lines at least.
Okay.
I could go up to 50. No, it was a ton of lines. This was just, there's so many lines you can't actually picture it because
Right,
otherwise
so this was
you would
just
be
illustrative. It was, yeah.
Yeah.
Okay, thanks. Matt.
So I wanted to just say that I appreciate that you're starting with the magnetic fields as a motivation for this work, because often we astronomers are well, we don't really know what's going on. It must be magnetic fields. So good on you for inverting that. I actually had a question that was kind of related to Alice's, because I have on occasion struggled to do photometry, even broadband photometry of K-stars. It seemed like you were working with K-stars. And what I've been told is that they're difficult to understand because they have so many lines. But it seemed...
That's an advantage, come on.
That's what it
okay, so maybe I've been told a fable. What do you have an opinion on that?
I mean, there was a ton of lines. So that's the thing of like, one thing is like, you don't use all of the lines for multiple different reasons. There was the tellurics, there was absorption lines, but there's also the models themselves might not completely be accurate. So that's why we like select specific specific spectral features. Is it also has to be the model can actually line up. Like there are some spots and some of the different ones that were kind of interesting of like the model would all of a sudden have a line and the data didn't, or the data would have a line and the model didn't. So there's definitely like weird kind of stuff going on. But there is a lot of lines, and there's a lot of like shallow lines and a whole lot of kind of like if you tried to fit every single line you saw, it would be insane.
Did you find any trend with subtype within your? So I think all your stars were Ks.
Ks and Ms for the most part.
Ks and Ms. So did you find it easier to fit Ms versus Ks, or do you find the fits were better with any subtypes? I'm just curious.
I don't think specifically within subtypes because there's so many different variables of also because there's different nights of observing. That also changed the spectra because of the Earth's atmosphere, as well as just other things possibly with the star itself. Yeah, so there's just a kind of a lot of different stuff going on. I wouldn't say that I noticed one specifically with the different spectral types. It was more like each star had its own battle, honestly.
Which was your nemesis?
Which was my nemesis? The one star that's not on here. There was a star we used for calibration of AU-MIC, and that was half of the program. I was spending time trying to do it because we were using that as calibration between Spiru, which was what used in previous papers, and with these tools, and WINERED. And that was the one star we were able to actually like have both in. And yeah, I spent like 4 or 5 weeks trying to run spectra analysis on that star, and it still was not. It was still acting weird. I literally almost punched the computer multiple times, I'll be honest with you. I was like,
Oh, okay, thank you. So I completely forgot to set up for online questions, but Matt is way ahead of me. Matt, what is the online question?
Well, I'll just summarize. The spirit of the question is whether your linear superpositions of magnetic field solutions tended to favor one particular B value, or were more evenly distributed?
I would say evenly distributed. So overall, we had a range of 0.059 to like 4.315 or something like that. So there was a range of magnetic fields. I would say most of the time, your 0 kilogauss and 2 kilogauss were probably the ones that were the highest the most, but that was just because we had a lot of low magnetic stars. But there were other ones that like 4 and 6 got actually pretty decent numbers, and that's the one like it moved up into like the average magnetic field was like 4 point something. So there was a good spread over, because that's one thing we were checking for.
It might be interesting to do a plot for each star of like the A values. You know, so like versus like a little histogram of A0, A1, A2, just so that you can see how the fit distributed them.
Yeah, maybe like I mean maybe.
All right, time for one last question. Yes, Christine.
Would you be able to explain, I believe you called it the velocity factor, I just wasn't actually familiar, and I know that it was the period of rotation divided by tau, but what is tau?
Tau is the convective overturn, which is the amount of time it takes for for the convection current to make one cycle. So because that's an important part of the dynamo process, and as well as the rotation. Yeah, time.
So they're both times.
They're both times,
So
yeah.
it's just like unitless number then?
Yeah, it's unitless, so that's why there's no units on this, because you're literally divided by the same thing. But yeah, I didn't know what it was either before this, so.
So it's sort of like, I mean, well, maybe you can comment a
Not
bit.
saying anything with it.
Well, I would like to know, is it like a how turbulent things are number?
Yeah, and how much mixing is going on.
How well mixed it is?
Yeah.
Yeah, like if the convective overturn is like
Yeah.
smaller number, it means it's going through the cycle faster, and vice versa. So that's why you have to have both, because then you get like the full actual dynamo kind of effect going on. You're accounting for the whole thing.
Okay. Fantastic. Thank you again, Julie.
Right here.
Nice job.
So now we're going to move just a little further out from the sun, and we're going to go sort of earlier in the life cycle of the star. We're going to be talking about protoplanetary disks. And so our next speaker, last one before the coffee break, folks, is Tarisai Dziire.
Tarisai Dziire.
Dziire. I'm
Dziire.
sorry, I didn't really.
That's okay.
Yeah.
Wait, is this on? Can you
Not
hear
yet.
it?
Flip the switch.
Hello? Hello? Hello?
Oh, that's right. Yeah. Well done. Awesome. So Tarisai is from New York University, Shanghai, and has been working this summer with Jenny Calahan and Karen Oberg on protoplanetary disks. Tarisai, I'm going to turn over to you for tell us all about that.
Okay, hi everyone. I'm Tarisai Dziire. Like Jonathan said, I'm from New York University, Shanghai. And this summer I was working with my advisor, Jenny Calahan and Karen Oberg, on accretion and protoplanetary disk and its impact on volatile snowlines. So, starting off with protoplanetary disks, we need to start at the beginning, specifically the star formation process. So, stars form within the dense regions of a molecular cloud. And so, over time, these super dense regions will collapse in on itself due to the strong self-gravity of the cloud and form a hot protostar. So in order to conserve angular momentum, a circumstellar disk is created, and in this disk envelope phase, the disk serves to funnel its material to the protostar, helping it grow in size. And then the circumstellar disk transitions to a protoplanetary disk where it hosts a suitable environment for planet formations. So why do we want to study protoplanetary disks? I'm going to refer to them as PPDs because it's kind of a tongue twister. But the main intention is that we really want to understand what's going on in our own backyard, our solar system. We want to understand how planets are formed. And here is a photo taken from ALMA, the Atacama Large Millimeter Submillimeter Array Telescope in Chile. Here we're looking at PDS-70, and to the right it's PDS-70c. It's a young Jupiter-like planet around 400 light years away from us. And as you can see, this is direct evidence that planets are forming within PPDs. You can kind of see over here, wait, I think there's a pointer. Let me use the pointer. Yeah. You can see over here how we're looking specifically at the dust of the protoplanetary disk. It's taking some of its material and helping the planet grow in size. So now let's take a closer look inside PPDs, starting off with the host star. So the host star acts as the primary heating source of the disk. The heat from the star will penetrate the disk, so as you get further away from the host star within the disk, temperatures will start to decline. And then accretion is another heating mechanism of the disk. Accretion occurs when material of the disk has internal friction. So the particles are rubbing against itself, and then this will cause a loss of angular momentum. So when angular momentum is lost within the disk, some of its material will start to spiral inwards towards the star. And as this material is spiraling inwards, gravitational potential energy is lost in the form of heat, which is why accretion is another heating mechanism. And then zooming in towards the midplane, this is where temperatures will start to decline. And so gas will start to sublimate into icy grains. And this is where you'll find our ice lines or snow lines. It's a really critical region for planet formation, which I'll reinforce in the next slide. And so looking closer within the disk, this is where you'll start to see the aggregation of large dust grains. They're on the order of 10 microns. So if you look at your strand of hair, a large dust grain is about 6 times smaller than a strand of hair. And so why are these snow lines critical for planet formation? So in the top left figure here, we're specifically looking at the water snow line. So when you're right outside the water snow line, these ice grains will freeze out onto the dust. And so this will change a lot of properties of the dust, specifically how sticky it is, and this will really help contribute to grain growth. And then so eventually, over millions of years, these grains will grow into larger terrestrial bodies, really important for planet formation. But when you're right inside the water snow line, there will be more efficient fragmentation. So more of these dust particles are going to break away from each other, but because of the increase in pressure within the water snow line and the surface density, we're still going to be looking at Mars-sized embryos will start to form, as you can see in this figure here, over time. So the water snow line and other snow lines as well are really critical for planet formation. And then if you look in this figure here on the right side, we're looking at the carbon and oxygen ratio as a function of radius from the star. So by looking at the carbon and oxygen ratio within exoplanets, for example, we can map out where in their initial PPD they formed and infer other things on its planetary composition. So the main question that we want to answer is, how does accretion impact our snow lines? And so we answered this by using a thermochemical modeling code, DALI. And to make sure that DALI is really exhibiting the fundamental physics that we see within heating mechanisms from the star, we compared DALI's temperature structure to an analytically derived temperature expression. And then after this, Jenny implemented an accretion module where I was able to manipulate the accretion rate and see how it shifts these three volatiles: carbon monoxide, water, and carbon dioxide. And just for reference, a volatile is a molecule that vaporizes relatively easier at lower temperatures. So the model that we ran, we're looking at a 0.6 stellar mass star, and we ran 3 different disk mass models: 0.1%, 1%, and 10% of the stellar mass. So let's take a closer look into DALI, the thermochemical modeling code that we use. So DALI initializes by taking in a set of parameters that govern, for example, the mass of the star, the mass of the disk. And then it maps all of this out on a 2D calculation grid, as you can see here in the R and Z space. So from cell by cell or point by point, it will calculate the temperature of the dust through the dust radiative transfer process and thermal balance. And so within the thermal balance, there'll be molecular excitations that will govern the gas abundance and gas temperature of the disk. So right here is plotting the figure of our analytical temperature structure that we used. So this expression assumes that the disk is vertically isothermal or optically thick. So as you're climbing to a higher radius and the height of the disk, we're looking at temperatures, we're looking at same temperatures. And then we're also assuming that the disk is geometrically thin. And so shown here in green, this is the passive heating temperature expression that we use. So passive heating just refers to heating from the host star. And then in red is heating due to accretion, and then the blue curve is just an effective temperature expression that combines both of these. So as you can see, accretion heating dominates as the primary heating source within the inner regions of the disk. And this model specifically with an accretion rate of order of -9, you can see that accretion heating is dominating within around, I think this is like 0.3, 0.4 AU. And so now we want to compare DALI's temperature structure to the analytical temperature structure, because this is really modeling the fundamental physics that we see. And so as you can see, DALI shows great agreement with our analytical temperature.
only deviating around 0.25. And for the highest disk mass model, shown here in purple, while all the disk mass models are really close in agreement, the highest mass model shows more agreement, and that's just because there's more material, meaning that this disk is more optically thick, which goes back to what the analytical temperature structure is assuming. So here, we wanted to see how increasing the accretion rate changes that radial location where accretion heating is dominant. So on my y-axis here, I'm taking this intersection point shown here, where passive heating and accretion heating intersect. So within this R radius is where accretion heating is the primary heating source, and then past this radial distance is where you'll see passive heating, the heat from the star, act as the main heating source of the disk. So as you can see, as you increase the accretion rate within the disk, it pushes back that radial boundary where accretion heating is dominating, and it does this even more dramatically for our higher disk mass models. And so we also wanted to answer, like I said in the beginning, how the accretion rate is changing our snowline locations. So how we defined our snowline, we took, for example, the ratio of gaseous or water vapor to its ice form, and we wanted to see where this ratio equals 1, as you can see here in this blue dotted figure. So within the snowline, the area under this line, this is where you'll start to see water in its iceous form. And then just right above the snowline, this is where you'll start to see water in its vapor form. So starting off with water and carbon dioxide, you can see that as you increase the accretion rate, it will shift the water and carbon dioxide snowlines further in the disk. And it does this more dramatically again for our higher disk mass models. And then looking at carbon monoxide, for the lowest disk mass model, it is not vulnerable at all to the accretion rate, and that's because the snowline location is around 20 AU. But if we go back, and if we're looking at the lowest disk mass model for the red scatter points, for the highest accretion rate, accretion is only dominating as the main heating source at a max of around 10 AU, but the CO snowline is at 20 AU. So the heat for the disk is mainly coming from the star itself and not from accretion. So that's why we're not looking at any effects. But as we see with the higher disk mass models, accretion will start to have an effect on the CO snowline. So we also wanted to see the temperature at which the water snowline is. So we looked at some literature, and we found that water has a condensation temperature of around 150 Kelvin, which you can see is modeled by this red contour line. So as the water snowline, shown in black here, as it climbs to higher regions within the disk, it really prefers the 150 Kelvin condensation temperature. But if you look here closer to the midplane, the first appearance of the water snowline, it shifted a little bit backwards of this 150 Kelvin temperature. It's actually at a higher temperature, and we're still trying to configure as to why the water snowline at the midplane prefers these higher temperatures. So in conclusion, we saw that Dolly's temperature structure agrees really well with our analytical passive heating temperature expression, and that the radiolocation of the snowline is pushed further back in the disk as the accretion rate increases. And so we see this with water and CO2 for all of the disk mass models, but we only see this relationship for the CO snowline and the higher disk mass models. And just to give a bigger scope conclusion, why do we want to look at the accretion rate? So if we're able to detect what the accretion rate is in a PPD through observations, then we can kind of predict where these snow lines live within the PPD. And then from this, we can kind of predict or map out where we expect to see these planets form, and then from its snowline locations and maybe from some more JWST observations on the molecular abundances, we can kind of come to a conclusion around its planetary compositions. Okay, thank you. Wait, before questions, let me get my water.
Thank you very much indeed.
Okay.
Chris had a very nice job. So yeah, now that she has a water, questions for Tarisai.
So maybe I missed it, but did you mention how we measure these accretion rates observationally, perhaps? And have you, if that's been done, have we been able to compare that yet, or do you plan to, against these Dolly or these analytical temperature measurements?
So I haven't really researched how we're able to measure the accretion rate within PPDs, but hopefully when I work with Jenny more after this program, maybe we can research how they're able to do that and put that into our model, so it's more, our data that we're getting is more aligned with what we see in observations. But yeah, good question.
Maybe I missed it, but what kind of star did you assume was the source of all of this?
So we use a 0.6 stellar mass star, so around
I'm sorry,
half. So around half the mass of the sun. That was our star that we used.
Okay.
Yeah.
Yeah, 0.6 wasn't it?
Yeah, 0.6. Yeah, okay. Because it would be fun to do it for different masses, because those give you different, different environment.
Yeah,
different
yeah.
And then also too, that might affect the kinds of planets, the flavor of the planets that form around them, depending on where you're snowlined, etc.
Yeah, so that was something that I was interested in playing around with in Dolly, but for the summer REU, Jenny just wanted me to play around with the mass of the disk first, but I agree, yeah.
Yeah, if only the REU was 20 weeks instead of
I don't know about that, but yeah.
Oh, we have great ideas, come on.
I know, I got serious. Yes.
That was a really nice talk.
Thank you.
I wondered if you thought about the time dependence a little bit, because accretion rates are a variable, but they should probably also decrease over the lifetime of the stars. I wondered.
Yeah, so I think, so going back here, how I was saying that, or maybe I'll just show the accretion. So when Jenny actually implemented the accretion inside Dolly, it's just an analytical equation. And I'm pretty sure this equation assumes that the accretion rate is constant over time. Yeah.
Any last question? Matt.
No, go ahead.
Can you show your slide 9 again? I think it was 9. Yeah. So, great talk, by the way.
Thank you.
There's a lot of structure reflected in all three of those curves, and I was just wondering, is that meaningful structure? All those vertical excursions in each of the three curves as a function of radius, or is that just transitory and that would?
Are you talking about like the little squigglies?
Yes, like up, down, up, down, up, down.
Yes, that's what I'm talking about.
I think it's probably just due to the fact that, so here we're looking at the midplane because the passive heating doesn't really take Z into account because it assumes that throughout the height of the disk the temperature is the same. But within Dolly, in my code, I didn't exactly choose the temperature where Z is equal to 0. I kind of chose like a range of Z where it's just very, very close to 0. So that's probably why you're seeing like where it goes hot, cold, hot, cold, hot code. Yeah, it might be numerical noise, and also with Dolly, since it's not assuming that the disk is optically thick everywhere, as you're climbing to like the atmosphere, you'll start to see a rise in temperatures. So that could also be a reason why it's fluctuating a lot. And also the density as well.
Thank you.
I think you had a question too.
Yeah, I was just thinking those low mass stars flare a lot. I mean, really a lot, which is going to change the radiation field.
That is
a
true.
lot, frequently. Which, yeah. And have you compared it, or would you compare it to anything that we observe in detail? I mean, I'm thinking of TW Haya, which is a low mass star, and we see the disk face on, where you could really compare your models to the real world.
I think actually in the beginning when I was creating my graphs for this analytical temperature structure, we were looking at TW Hydra. But in terms of your question of like how I would be able to model how the star is really fluctuating, I'm not really sure how we would try and include that into DALI. Maybe DALI has something within its code of how it's shooting out these photons to model the radiative transfer process. I'm not really sure, but I think DALI takes something within the star. It has some set of parameters to really model what we would actually see.
The question is, what is the time scale on which the PPD adjusts to a change in, right? If it adjusts quickly to a change in radiation, then you can just run the code with different values.
Yeah.
But if it's a slow response, then you have to do something cleverer. So that's an interesting question.
No. Oh, that's nice.
Yeah, I think that's really in the heart of the code, which I don't really super understand what's going on there, but hopefully I answered your question.
Fantastic. So now we have a 10-minute break. There's plenty of coffee and bagels and stuff still to be consumed. And we'll resume at 11:20 with Abigal. All right, our second session, we're going to go a little further out into the galaxy, and then we're going to get to nearby galaxies. And so our first talk in this session will be by Bohl from Cornell, and who has been working with Catherine Zucker and Theo O'Neill. Theo here?
Oh, Theo's not here, but she's they're watching online.
Hi, Theo. Yeah, Abby came to us from Cornell. She's going to be telling us about the size-linewidth relationship of molecular clouds in 3 dimensions. We'll just get set up here. Ready to go?
So, oh, actually, no. How do I put this on? Oh, there's a clip. Whoa.
That sounds on.
Yeah.
Let's just go here. Wow, that's cool. Wait, is this working?
That is working.
Awesome. Okay. Well, hello everyone. My name is Abby or Abigal Bohl, and I'm going to be talking about reevaluating the size-linewidth relationship of molecular clouds in 3D. This is a project I worked on with my wonderful mentors, Catherine Zucker and Theo O'Neill. So, yeah. So just a little outline of what I'm going to be talking about today. So we're going to start with talking about what is a molecular cloud, what is the size-linewidth relationship, then move to talking about what we actually did for this project, then we'll talk about the results, and conclude with a brief recap. So what are molecular clouds? So molecular clouds are a type of interstellar cloud that consists of structures of dense gas in the interstellar medium. So this is a picture of the Perseus molecular cloud, and this arrow here points to some of the intricate structures of dense gas in this cloud. Most of this gas is molecular hydrogen, which is typically difficult to detect, so carbon monoxide, or CO, is used as a tracer for these structures. So one of the reasons why molecular clouds are important is because they're the site of star formation in clouds, and so you can see that from this arrow, but where is that pointer? Here it is. You can also see it at other points in the, aha, perfect. You can also see other sites in this cloud as well. So here's some of those structures and then star formation within those structures. So since stars form in these molecular clouds, the properties and structures of molecular clouds play a role in the evolution of molecular clouds and how they convert that gas into stars. So some of those are a little bit complicated to understand. So key measurable properties of interest include the observed size, the velocity dispersion, and the mass surface density. So accurately measuring these properties and determining the relationships to each other is necessary for understanding and predicting the star formation process. So the Larsen size-linewidth relationship is a trend identified in molecular clouds that relates the size of the cloud to its velocity dispersion, or its line width. So you can see on this graph right here, each one of these points is a molecular cloud and its respective size and its line width. And so you can see that there's a pretty clear power law trend right here between these clouds. So this trend has been continually re-examined since its initial discovery in 1981 due to its implications for structure and turbulence in molecular clouds. So having this consistent power law scaling across a variety of environments and stellar activity levels suggests that there's some sort of universal underlying physical process that drives the dynamics of the interstellar medium. So from this power law relationship, we can gain insight into the nature of turbulence in molecular clouds and its implications for star formation. This trend, however, was identified in 2D, or position-position space. So in 2D space, size is measured along the plane of the sky. So in this graph right here, we have 2D space. So this is what the Perseus molecular cloud, which you may remember from a couple slides back, would look like from Earth. So size is this blue line measured along this axis. And then velocity dispersion is measured into the plane of the sky. So these are essentially little arrows that point into the sky. So in 2D space, size and line width are not measured along the same axis. In 3D, or position, position, position space, we have position, position, position. We can choose how we want to measure size, since we have the structure of the cloud in 3D. So we can choose to measure size along the same axis as velocity dispersion. So here we have both size and velocity dispersion going along that same axis. So size and line width are measured along the same axis.
So up until recently, the depth and internal structure of molecular clouds has not been measurable due to large distance uncertainties. So therefore, prior studies such as that Larsen-Linewidth relationship have been on the Size-Linewidth relationship in a 2D space, or a false 3D space with velocity as the third axis. However, parallax measurements from Gyure 2 and Gyure 3 have allowed the creation of true three-dimensional dust maps of nearby molecular clouds. And so these new maps allow us to reevaluate that Larsen-Size-Linewidth relationship in true 3D space by measuring size and line width along the same axis. So how do we actually do that? So measuring the size-line relationship, we need data for the size and the line width. So in red here, we have this Leakey et al. Dust extinction map. So brief aside, what is dust extinction? So dust extinction is essentially the scattering of electromagnetic radiation by dust between an emitting object and the observer. So what that means is that when there is dust between a background star and the Earth, some of that light is scattered, and the light that we see appears redder than it actually is because blue light is easier to scatter. So since we now know the distances to these background stars from Gaia parallax, we can use the reddening of light from different background stars to determine the structure of the dust that therefore must be between that background star and the Earth. And from that, you can create these 3D extinction maps. So the size of the cloud along each line of sight can be determined by considering the dust extinction as a function of distance along each line of sight. So here we have the dust extinction curve, its distance, its extinction, and so this right here, this curve, that will be our size. In blue, we have the Dame et al. CO map. So this is the CO map down here. And so velocity dispersion can be determined by decomposing the CO spectra here into different velocity components. So these figures on the left right here are, as I said, are the dust extinction map and the CO map. This is just integrated dust extinction density and integrated CO density, so you can kind of see the shape of the cloud. Here we have those two maps overlaid, and then at different specific coordinates, if we were not integrated, then at these points, this is what the dust looks like, and this is what the CO looks like. And so you can see that they change a little bit across different coordinates in the cloud. Okay, so methods. So how do we actually find this 3D size-line width relationship? So the size and the line width will be the standard deviations of Gaussians that we fit to the CO spectra and the dust emission curves. So first we take the dust and CO data and then run it through this Gaussian decomposition algorithm. Another quick aside. So since decompositions of Gaussian functions are not unique, so what that means is that you can essentially fit multiple different Gaussians to the same set of spectra here. These Gaussian decompositions are sensitive to the initial guesses for the number of components. So the components, the number, the positions, the widths and amplitudes, the decompositions are sensitive to these initial guesses. So instead, we use the autonomous Gaussian decomposition algorithm to eliminate that subjectivity in the initial guesses. So what this algorithm does is it calculates the properties of the Gaussians by taking derivatives of the spectra. The clicker's giving out on me. Oh well. So it calculates the numerical derivatives of the spectral lines and then smooths those because of the presence of spectral noise with a regularization parameter. And so supervised machine learning is used to train this algorithm to select the optimal regularization parameter based on a training data set. And so we use an autonomous Python implementation of this algorithm called GaussPy+. So we train this algorithm on Perseus data, and we get these Gaussian decompositions for each line of sight. I wish that this clicker worked. Oh, it's back. OK, perfect. So red is dust again, and then blue is CO. And so at each point, each one of these, as you can see on this line here, is a number of Gaussian components that we recover from this algorithm. So each one of these is one line of sight. And then so these ones right here are what those lines of sight look like, and then Gaussian fits to those lines of sight. So we exclude lines of sight that have more than one Gaussian component in either dust or CO. So this third CO spectra here, you can see has two peaks in CO, which makes it more difficult to compare to this dust extinction curve. So we just exclude that line of sight and then all other lines of sight like it. So you can see in this one here, these are the points that remain that have one line of sight in both CO and in dust. So if you're looking at here, you might notice that there are some lines of sight that are not included in this molecular cloud. And so what we do is since carbon monoxide is a tracer for these clouds, we exclude points that have a low amplitude in CO. So right here, this is low amplitude, so this one might correspond to any of these points up here. But we don't want those, so we exclude based on a CO cutoff. So we just want to get those points in the molecular cloud. So after these exclusions, we are left with a smaller set of points that we will then use to find the size-Linewidth relationship. So here, this is those final points. This is an example of a set of spectra and dust extinction curve that have fit our final exclusion parameters. So we will then fit a best fit line to those points using a least squared regressions fit. We will then repeat this process on the Cepheus and Taurus molecular clouds. So Cepheus here is the top row. We have the integrated extinction density. So Cepheus, Taurus, integrated extinction density, and then these are the Gaussian line of sight fits, and then the final set of points that we use for our final best fit solutions. So you might notice that Taurus has fewer points here, and that is just because a lot of the points in the Taurus dust extinction fits have more than one Gaussian component. So we have to exclude the majority of those lines of sight. So this is what we find. We find a 3D size-Linewidth relationship of 0.09 times the size times to the power of 0.025, and so that looks a little bit like this. And so this is the combined size-Linewidth relationship that uses points from all three of our clouds. So you can see at the top right here, Cepheus, Perseus, and Taurus, and those different colors correspond to the different clouds. So while we find that the size-Linewidth relationship still holds in 3D, as you can see from this figure, this 3D curve is shallower than the original 2D Larson size-Linewidth relationship. So as you can see that right there. So what that means is that turbulence is still consistent on different size scales, but future work should look into what this shallower curve means for turbulence in molecular clouds. And so just to recap, so stars form in molecular clouds, which are these complex structures composed of dense gas in the interstellar medium. We re-examined Larson's size-Linewidth scaling relationship using 3D dust extinction maps of local molecular clouds. By applying Gaussian fits to 3D dust extinctions and CO spectral maps, we find an average size-Linewidth relationship of sigma v equals 1.09 times L to the 0.25. And this satisfies the Larson scaling relationship, though our derived power law slope is shallower than comparable slopes identified solely through spectral line maps. And so yeah, that's all that I have for today. Thank you so much for listening, and let me know if you have any questions.
Thank you, Abby.
So, Abby, this was such a great talk. I don't know anything about this. This is great. Looking at the last slide you showed us right before this, it kind of looks like your fit, like, depends a lot, maybe on that last point all the way to the left. Is that fair for me to say? Is it robust to, if you...
Which one? Is like this one?
This red one?
Yeah, that guy, John.
Yeah.
I'm just wondering if it's robust to like resampling the points you have, or you've looked into understanding, quantifying the uncertainty to make sure that you really are distinct from the 2D of it.
Yeah, so I think one of our future next steps is going to be quantifying uncertainty. So one of the things that we looked at is the fact that there is a little bit of scatter here. So due to the time constraints of the program, we didn't really have time to delve into quantifying the amount of scatter, but just by looking at other fits, the Larson one, as you can remember, maybe did not have so much scatter, but I've seen other ones that have a similar amount of scatter. So yes, so all that to say is that there's different amounts of scatter that people find in different studies. So this one does have comparably more scatter, and that fit there, or that point, I suppose, maybe plays a role in it, but I think in future studies
you might want to try
into
throwing out occasional outliers and see if you get the same answer. Question?
Just really great talk, Pat. Do you have a sense of how much which parameters have changed compared to the original Larson ones? Is it the line width has changed more, or is it an estimate of the size? Where do the other points lie here, and how do you pursue it?
Oh, okay. I'm actually not entirely sure. I don't know. I think what you would have to do is just overlay the points, I suppose. And I haven't particularly done that, but I think that that's a really great thing to look at in the future as well. So yeah, thank you.
I'll ask one as well. Along the same lines, with this data set, you could do the PP analysis on this data and show how much of the difference from Larsen is just you have a different sample, and how much really is the projection. So that might be interesting to do.
Yeah, I would agree. Yeah.
Thanks for a very interesting talk. I'm interested to know, since part of the importance of Larsen was its claim to be universal, whether you think it would be necessary to retrain your model on every single complex, or maybe classify the complexes and retrain by class, or if you could make some claim yourself to apply this universally. That would be very interesting.
So complexes meaning like the different clouds?
Like Taurus or
yeah, so I think
Perseus.
what we would like to do, I think, is retrain the model on different clouds. So we kind of have a limited set right now. We only did 3. We're hoping to expand it in the future to more of them, including training them on those individual ones. But it was kind of just another time constraint. So I think future work will include that as well.
Kaylee.
Is it surprising that Larsen had such little scatter, or like surprised that would be a lot more scatter? Like, is there any sort of like intuition or expectation around that?
Well, when I looked at it, I thought it was surprising initially, but I think that what people have done is that they said that, wow, that's actually very interesting that there isn't, not necessarily scattered, but that it fits this law, and so that's why people have been re-examining it a lot, I think, over the past, how long has it been since 1981? It's been a while.
Not so long.
it's been like a couple years, but yeah, it has pretty interesting, I think, implications for like what that means physically, and so what's happening within these clouds. Turbulence is, I think I talked about a little bit, is one that people have been continually like retouching on, and so what is driving these physical processes to make it such that there's a relationship between size and line width. So it appears there may be some universality within that. So yeah, it's an interesting relationship, to answer your question.
1981, when I was a summer intern. I think we'd better move on. I was going to get it right.
Okay.
Yeah, I realized that all summer I've not been ever saying people's last names out loud.
Well, the last name I'm used to. The college I was surprised by.
Yeah. All right. It's right on the website.
Just a second.
Yeah, let Christine get set up.
All right, can you hear me? Okay, and then...
So our next talk is going to be by Christine Gyure from the University of Richmond. and she has been working this summer with Katie Brauer and Ashley Villar, and she has been looking at reproducing our process enrichment in ultra-faint dwarfs with only binary neutron star mergers.
I like the emphasis on only.
Yeah. So, Christine.
All right.
If you are wearing any gold or platinum jewelry in the audience today, this was originally made through the R process, or the rapid neutron capture process. This is a nuclear reaction that's responsible for a lot of the heavy elements that we know and love today, and it's characterized by successive neutron capture before the nucleus experiences significant radioactive decay. The R process is super important because, as I said, it creates a lot of the heavy elements that we see and use today, but there's a lot of debate about the origins of the R process and where perhaps it might have been formed. And so we get it down knowing that we have a need for a neutron-rich environment for this process. We have two prevailing theories, and this would be core collapse supernova and more interestingly, the only confirmed area of R process creation, R process element creation, neutron star mergers. Neutron star mergers are small, dense neutron degenerate cores of supernova. They often form in binaries and then experience orbit decay until a fantastic merger explosion you're about to see, where it emits R process way out into outer space. And this is the only observed confirmed source of the R process. And if a neutron star merger happens within or close enough to the galaxy it originates in, it can enrich the stars within the galaxy so that their spectra include these R process elements whose origins we want to understand. The thing is, even though neutron star mergers have been treated as the primary source of R process enrichment, there are a couple of issues regarding the properties of neutron star mergers and whether they might inhibit their ability to enrich, in particular, small dwarf galaxies. The first one is the natal kick velocity. This is initial velocity due to asymmetries in the progenitor supernova. And the second one is the delay time, which is the time in between when the neutron star binary forms and in between when the merge happens. And so you can imagine, again, particularly in the limiting scenario of a small dwarf galaxy, that if the kick velocity is too high or if the delay time is much too long, your neutron star merger might get kicked out of the galaxy, not retained at all, and not contribute to any R process enrichment. And so, looking at this limiting scenario, we have some candidates. Ultra-faint dwarfs are a very interesting case study of this. They're small, dark matter-dominated halos that are relics of the early universe. And you can see kind of a size comparison of a satellite dwarf halo to a Milky Way mass galaxy. And the thing about these dwarf halos is that their escape velocity is so small that it's pretty easy to imagine a neutron star merger forming in one of these ultra-faint dwarfs might have feasibly enough of a kick velocity or delay time to thus not really enrich it. So there would be a reasonable expectation, okay, maybe there's not that much R process enrichment in ultra-faint dwarfs. However, we know that they can be enriched because we've observed it. And in fact, we've observed of the 20 ultra-faint dwarfs for which we have very good spectra, we've actually observed that 3 of them have moderate or heavy R process enrichment. And in fact, ultra-faint dwarfs are great candidates for studying the R process because due to their relatively small and simple nature, they record chemical signatures from these R process events really, really well. And so a little bit of nomenclature here. If an ultra-faint dwarf is not enriched at all, we call that R-no, there is no enrichment. If it's moderately enriched, this is the level of R1 enrichment, and then the highest level of R process element enrichment is R2. And we notice that around our very own Milky Way, we have 2 moderately enriched halos. This gives an R1 fraction of 10%, and 1 heavily enriched halo, and this is an R2 fraction of 5%. So given the fact that we have, in fact, observed R process enrichment in ultra-faint dwarfs around the Milky Way, we know it can happen, and we also know that neutron star mergers are the only confirmed source of R process element creation. We want to understand to what extent neutron star mergers are in fact responsible, given that they have these possible limiting, constraining factors of natal kick velocity and delay times that could send a neutron star flying out, right? And so the way we go about this is we created a novel analytic model to connect the natal kick velocity and the delay times of a bunch of sampled and simulated neutron star mergers to predict the chemical enrichment of a bunch of small dwarf galaxies. The first step, of course, is to use simulations of satellite dwarf galaxies similar to the ones we observe. And then we begin our stochastic model, which takes in 2 distributions. One for natal kick. We use a Maxwellian velocity distribution that takes in 1 parameter, the width, sigma. And then the delay time distribution, which is a power law. We know this from fitting a distribution to gamma ray bursts, which are attributed to neutron star mergers. And this takes in 2 parameters, the minimum delay time and the exponential index alpha. After having these 2 distributions, we get what we're really interested in, which is how far away from the center of the ultra-faint dwarf, this is known as the offset, does the neutron star merger occur, if it occurs, you know. And so to do this, we created an offset distribution based on a bunch of repeated samples of the fact that we have a v, a natal kick velocity, and a t, a delay time. And it actually comes down to everyone's first high school physics relationship. Distance is equal to velocity times time. And so you can see we have a resulting sampled product distribution of velocity and time, where we have offset in kiloparsecs on the x-axis and our probability density on the y-axis. And then this is the really fun part, because using our sampled offsets of neutron star mergers relation to the center of ultrafaint dwarfs, we are able to predict the amount of enrichment that that halo will experience as a result. So here are 3 of the scenarios to kind of demonstrate those 3 levels of our process enrichment I have been talking about. The first one is if your neutron star merger occurs very close to the center of the halo. You can imagine it occurring, frankly, a lot closer than it is in this animation. And this is the highest level of enrichment, R2. The second idea would be vaguely if it occurs at or around or a little bit beyond the virial radius of the ultrafaint dwarf. This would contribute to R1 enrichment, moderate. And then the situation we are most concerned about would be if the natal kick and the delay time, or one or the other, is high enough that your neutron star merger occurs way beyond the virial radius. Imagine it much further than it is in this animation. And ultimately contributes to no heavy element chemical abundances at all. And so now that we have a model that takes in natal kick and delay time and then calculates a distance distribution, and then we're able to use that distribution to predict for all of our simulated dwarf halos the level of chemical enrichment, we start at the end and actually go backwards. Because what we want to see is if we can reproduce what we've observed, that 10% R1 fraction and that 5% R2 fraction, by setting our observed or our predicted R process enrichment fractions to 10% and 5%, and then inferring what the parameters are to the Maxwellian and the power law distributions, AKA for what natal kicks and delay times do we reproduce what we have seen around the Milky Way in our dwarf halos. And so really interestingly, this is the fun part, we actually can, in fact, successfully reproduce observed R process abundances. And this was in no way a given. It was very possible that we found a very real result could have been that for every kick velocity and delay time, the neutron star merger was not retained by the ultrafaint dwarf and didn't contribute to this enrichment. But we found instead that for a variety of parameter combinations, spanning over the entire range of values we tested for each parameter, we can reproduce observed R process enrichment. And so this is a semi-arbitrary number of parameter combinations that we picked. We just picked the top 10 that minimized the loss. And what we're plotting is the predicted by our model versus observed R process enrichment fractions. So you can see for R1 enrichment, we have that 10% observed, and for R2 it's 5%. And roughly speaking, all of our loss minimizing parameters look roughly the same in terms of R process enrichment. And this actually is the case beyond just the top 10. It's more so for even the top 20 when we looked at them. And so to go a little bit into the behavior of each parameter, here I have 5 plots representing the 5 different parameters that we varied over. The first 3 I've already mentioned, T min alpha and sigma arise naturally from our input distributions. The last 2 are we decided to vary the maximum distance a neutron star merger could occur for the halo to be considered R2, and then the maximum distance it could occur, which is going to be further out, for the halo to be considered R1. And what we did is using one of those parameter combinations on the previous slide, we held all of these plots at those fiducial values and except the parameter of interest for that plot, and then looked at how it varied over the range for which we tested. And so what I've circled here are indeed the fiducial values that we held all the other plots at. And you can see that, of course, they are the ones that best minimize the loss. And this was, again, a rather arbitrary choice, but we could have made this plot for a lot of the parameter combinations to see how it varies with respect to the values we test it for. And so looking at the implications, this actually has very interesting science implications. Neutron star mergers alone can correctly reproduce the observed R-process abundances in ultra-faint dwarfs without the need of a secondary or additional source, such as core collapse supernova. And as I mentioned, the origins of the R-process are actually quite hotly debated within the field. It's either, no, it's neutron star mergers, or no, it's core collapse supernova, or it could definitely be both. But the interesting thing is that per our model, you don't actually need another source. We know that based on what we've seen, what we've seen that neutron star mergers do produce these elements, we could in fact reproduce observed abundances. So in the neutron star merger versus collapse R controversy, this is essentially +1 point for neutron star mergers. Although we say nothing about the likelihood of collapse stars actually contributing or not. They very well could, but we don't necessarily need them to. Future work will include identifying the optimal parameter sets that best minimize the loss and reproduce observed fractions. And then, after we identify those optimal parameter sets, identifying just how realistic are those. Right now, we're varying each parameter over a very, very wide range. And we'll want to zoom in on the ones that we are positive are physically feasible. And so in summary, the R process, which is very important because it creates a lot of heavy elements, occurs in neutron star mergers. And we are looking at reproducing the observed R process enrichment fractions in the smallest ultra-faint dwarfs by varying the natal kick velocities and delay times, looking at the different properties of neutron star mergers to see if we can, in fact, reproduce observed abundances. We find that we can. And not only can we, but we can do it for a variety of parameter combinations, which could imply that neutron star mergers alone could possibly explain on their own the heavy element formation, the heavy element enrichment that we see today in ultra-faint dwarfs. Thank you very much.
Thank you, Christine. Questions?
Hi, that was a really nice talk. So I appreciate that you guys look at ultra-faint dwarfs to see where this is going to be most prominent, right? Are there prospects for measuring this kind of thing, like say like a Milky Way galaxy type galaxy?
Yeah.
Where you have like the bulge disk features. Like I imagine here, I assume it was probably like more random motions, like kind of all over the place. But where there was like a disk and there was different populations, like the bulge disk, for example. Like,
Yeah.
are there prospects for that?
No, absolutely. In fact, that was something that I originally had in the future steps slide, but
it's such an overarching picture that we ended up not including it for this specific project. But yes, this is very much step 0 of a much larger project to hopefully do the same thing for medium mass halos and ultimately Milky Way mass halos. You're right in that it would be quite a bit more complex. One of the reasons that we were able to do this whole D equals VT approximation, and actually a lot of the approximations that made this simple version of the model work is the fact that they were dwarf galaxies. But we do hope in the future to expand. However, obviously that's not something I was even able to touch this summer.
Jenny.
Do you know anything about the supernova rates in ultra-faint dwarfs? Would you be able to add that into your model?
I don't know anything at all. The thing is,
I'm going to be so honest. No, it is super interesting. It's very, very possible that both core collapse supernova and neutron star mergers contribute to our process enrichment. The thing is, since we haven't actually observed it coming from supernova, it's a little hard to move forward with that assumption. We could possibly factor in supernova rates, but I think we're starting with square one, which is just looking at neutron star mergers, and then fingers crossed with some of the observational periods coming up, we'll actually observe some R process elements coming from supernova. And then maybe we could, in fact, add that into the model.
Question?
Yeah, I have a question that is related to this one, actually. Imagine that I came up with a model for core collapse and that I could say, oh, I should have that much enrichment coming from this. That would mean that you have an overestimation of the enrichment coming from the mergers because you find something with magic. Is this plausible? Do you have an idea what could cause you to, for example, overestimate the amount of enrichment coming from mergers?
Yeah, well, I think one thing is the fact that we have such a small sample, And this is okay to do this approximation because it is essentially, for our purposes, we think it's a random sample. We actually are going to look into the possible biases because the 20 ultra-faint dwarfs for which we have good spectra for are the 20 probably brightest that we were able to, right? And so we don't actually know. One of the things we're going to look into is possible biases in the sample. It is possible that this is indeed an overestimate. And then also, of course, the simplicity of just saying, oh, well, there's 2 R1 dwarfs out of 20. That means 10%. Yeah, there are a lot of potential flaws with that. But knowing that based on all of the information we currently have, we can, in fact, reproduce those fractions. But more interestingly, we actually played around with a couple of other R enrichment fractions. This was actually by accident. We miscalculated the number of R1 enriched ultra-faint dwarfs. But originally, we were using 5% and 5% for R1 and R2 fractions, and we were still able to reproduce. So I think that for at least a small range in that area, this might actually still be the case, even if the numbers aren't exactly right and are indeed an overestimate.
Yeah, I mean, I was actually going to, that was kind of what I was going to ask, is in fact your 5% and 10% are based on 1 and 2 galaxies, and so it's really 5 plus or minus 5% and 10 plus or minus 5%.
Exactly.
And so actually, yeah, the agreement is even better than you.
Of course. But I think the point is, though, that when, again, this was kind of a happy accident more than anything else, when we had different enrichment fractions, this was still applicable. And that's something that we really can't do anything about until we have more data, right?
We need more data.
So
always a good mantra.
Fund us.
Oh, you actually already answered my question.
Okay.
Are there any others?
That was a great talk. Just a clarification question for me. How are R1 and R2 distinguished?
Ah, yes, absolutely. So it has to do with the ratio of the europium abundance in relation to iron. So it's a ratio. Basically, I mean, there's certain numbers. I think I can remember them, but that's not the point. Iron is the most stable element, right? And so we use it when we're calculating metallicity. We start with iron as our basis, and then we look at, in this case, europium, which we believe is an R process element only. We look at the ratio of europium to iron. And so there's a number, I think it's like, I don't know, 0.3 or something. It's 0.3 that distinguishes between R1 and R2.
So I wonder if it's just, is it like a continuous distribution between there's like, this is R1 and this is R2, but like there's a lot of cases that go through?
Yeah. There actually are. And I don't fully know, that is the definition that I have always understood, but I don't actually fully know how they came up with that. And I would be interested. It might be, that might be the case.
Oh, sorry, yes, good to
Hi,
hear
Denise.
that. Hi.
Great talk. This is kind of on the subject of you need more observations. I don't know what observations you would want to see to get better understanding of outer space.
Yeah, well, one thing is that as of right now, we've observed about 60 ultra-faint dwarfs around the Milky Way. We actually believe there might be upwards of 100, but we only have full spectra for 20 of them. So I think the next step, right, would be to get more spectra for those ultra-faint dwarfs around our Milky Way, which are nearest, that's the ones that it's definitely easiest to get it for, so that we have, every time we get more of a spectra, I suppose our R process enrichment fraction would become slightly more accurate, right? So yes, I believe that would be the next observations.
Thank you. I think we better move on. So thanks. And Hayden, you're up. So last talk before lunch. So our next speaker.
What do I think?
Don't ask me for help, I don't speak math. Do you want to center it more? There you go.
I'm new to this. Oh, there we go.
Perfect. So our next speaker is Zucker from the University of Central Florida. And Caden has been working with Kristen Hall this summer on molecular kinematics in dust-obscured AGN. Caden?
All right, so like Jonathan just said, my talk today is going to be about the molecular gas kinematics in dust-obscured AGN. Throughout the summer, I worked with my advisor, Kristen Hall. So the overview for this talk, oh, I realized I didn't put this, should I do that really quick? Yeah. Okay, is that better? Or, okay. Hello?
Yeah, make sure it's on.
Okay, is that better? Yeah. Okay, sure. All right, so the overview for this talk begins with the introduction, where I'll go over the basics of AGN, why are we looking at 12CO, 13CO, and 18N gas, and introducing our AGN data sample. Then for the analysis, I'll be showing our methods for probing their gas kinematics and their gas emission lines moment maps. And then to finish it up, I will go over our future work. So AGN, active galactic nuclei. Every massive galaxy hosts a supermassive black hole at its center. When material infalls onto a black hole, which is a process known as accretion, it is considered an active galactic nucleus, or AGN for short. AGN emit a significant amount of energy with observational signatures covering the full electromagnetic spectrum, from radio waves to gamma rays. Here in this image to the left, we have an AGN Centaurus A, and we can see in the smaller right images its emission in the X-ray, radio, and optical, just to illustrate what I just said. So why do we care about AGN? This plot to the right shows the number density of galaxies on the Y versus the galaxy luminosity on the X. Cosmological models have shown the trend represented by the red curve, and observations represented by the blue curve have shown different results. The observations have shown that the galaxy's luminosity has been less than theoretically predicted. To make the model match the observation, we need energy to heat the gas in order for the star formation to stop, which will limit the galaxy's luminosity. Or we could have the gas be expelled to limit the galaxy's mass, which is directly related to the galaxy's luminosity. AGN both describe these processes perfectly. So this exact process I'm describing is called feedback. Particularly, we'll be going over negative feedback. This begins with cold molecular hydrogen gas, which stars form from. As a result of accretion, the supermassive black hole launches outflows in the form of radiation, jets, and /or winds. You can see the outflows are like those cones, and you can see how it's directly interacting with that plane of the galaxy in the animation. These outflows heat the cold gas or even eject it entirely out of the galaxy. Once the gas is heated, star formation stops. And yes. So as mentioned, stars form from cold molecular hydrogen gas. H2 molecular gas is the most abundant molecular gas in galaxies, but due to their high excitation temperature, they are invisible in emission. 12CO is the second most abundant molecular gas in galaxies and has a low excitation temperature, so they are bright in emission compared to H2. So we can use 12CO as a tracer for this hydrogen gas, molecular gas, and use a 12CO to H2 conversion factor to figure out the amount of hydrogen molecular gas in the galaxy. So understanding the supply of dense gas, we can further understand the galaxy's star formation. To the right, we have a plot showing the Kennicott-Schmidt relationship. The axes show the star formation rate, surface density versus the molecular gas surface density. So as we can see, it's like pretty linear. As the molecular gas surface density increases, so does the star formation rate surface density. So what are we looking at? We're particularly looking for signatures of AGN feedback on the molecular gas in 10 Chandra X-ray selected dust obscured AGN. For this presentation, I'll be focusing on only one of these AGN, NGC 3079. And that's a really beautiful picture of NGC 3079. You can see the supermassive black hole is right in the very center, illustrated by the arrow. So we gathered our radio data that we used over the summer using the sub-millimeter array, which is an 8-element interferometer of 6-meter dishes near the summit of Mauna Kea in Hawaii. The SMA can be arranged into 4 configurations with baselines of up to 508 meters with different angular resolutions. So our particular sample was done using the compact and extended configurations. The SMA is great for observing our galaxy's dust continuum, 12CO, 13CO, and HCN molecular gas lines. So now on to our AGN. So this is NGC 3079. It is a nearby Edge-on spiral galaxy, which hosts a dust-obscured AGN. NGC 3079 has this super bubble, is what they call it, toward its supermassive black hole, which may be due to the AGN or winds released during starburst formation. You can see in the image to the left the structure of the super bubble zoomed in right there. To better understand the state of this interstellar medium, we will be looking at the thermal dust emission and molecular gas line emission. So this here is the thermal dust emission of the 230 gigahertz band data using the combined compact and extended configuration from the SMA. So by studying the thermal dust emission, we can understand the intensities that contribute to the energy output of a galaxy. Here in this image, we can see how close to the center we are observing. By like that little zoom in, you can see. This circle represents the SMA's field of view. In this continuum, the emission is fully resolved by SMA. And this is the 260 gigahertz band data. This was done using the compact configuration of the SMA. Here we can see that the maximum intensity in the color bar is higher than the 230 gigahertz band data was over here. We can also see that the emission in the image is partially resolved by the SMA. So here we have the spectral energy distribution, which is a plot of flux density versus frequency. The blue stars here represent the 230 and 260 gigahertz continuum emission that we just saw in the previous slides. The 3 black dots are from literature values from the Very Large Array, which is another radio interferometer that's in like New Mexico, which we use because the VLA has similar angular resolution to the SMA. We did a sample fit to these 5 points where the hashed line is the modified black body that the thermal dust emission emits, and the dotted line is the synchrotron emission. So synchrotron emission is non-thermal emission that originates from the AGN and or from the star formation in the galaxy. The best fitted dust temperature for the modified black body was 33.7 Kelvin, which is expected for cold dust emission. This plot can inform us on how much of the emission is coming from synchrotron emission or the modified black body emission. So in this talk, we'll only be presenting the analysis for the 12CO gases, but I also did similar methods to the 13CO and the HCN gas emission lines for the 230 and 260 gigahertz. So here we're looking at slices of a data cube showing the emission of the 12CO gas. These slices show us the systemic velocity structure of the 12CO gas in the galaxy from negative 270 kilometers per second to 290 kilometers per second. To further probe the gas kinematics from these data cubes that we just saw, we calculated their moment maps to visualize any asymmetries in the gas that could potentially indicate AGN activity. This plot shows the integrated intensity of the 12CO gas. This tells us the amount of gas at each pixel. So from knowing the amount of 12CO gas, we can convert to the amount of H2 gas using conversion factor, as mentioned earlier, which will in turn help us understand its star formation properties and then understand how the AGN may be affecting the galaxy. And here's the centroid velocity. This tells us how much the gas is moving away from us and how much it is moving towards us. This helps us to see if the galaxy has purely rotational kinematics or if there are any anomalies in the behavior of the gas. This plot here is showing us that it is a purely rotating disk. We haven't seen any asymmetries in the centroid velocity yet, and that will be a part of our future work. And then we have this plot that shows us the line width of the 12CO gas. This tells us about the velocity dispersion of the gas. We are still investigating this as well, part of future work, but there are interesting features to look at, such as like those extended arms you can see on the upper right in the red. So for my future work, I'll be working on line ratios of the 12CO, 13CO, and HCN gas, as well as making position velocity diagrams of NGC 3079 to help find any anomalies in the rotation of the gas. We'll also be looking at the Chandra X-ray data of NGC 3079. Here in this image, we can see the X-ray data and the 12CO integrated intensity that we saw earlier overlaid on an optical image of NGC 3079. And we can see in the X-ray contours, it's like kind of thin, the lines, but the X-ray contours, which is like the green and the gray, you can see like the structure of that super bubble I mentioned earlier. So really interesting things going on in there. And a little bit more from future work. So in total, we looked at NGC 3079 and NGC 4102 during my time over the summer, and we plan to continue the rest of the analysis with NGC 4102, similar to NGC 3079. After these two galaxies, we will move on to the other 8 in our sample data, and that's my talk.
Thank you, Katie. Questions?
Yeah.
Okay, so this is just me trying to understand how AGN is really affecting the galaxies. Could you go back to I think it was your first couple of slides? So there was a difference between a theoretical model. Oh yeah.
Yes.
One.
Yeah.
So could you maybe explain again for me how AGN is describing the processes, which is why the theory is different from the observations of brightness?
Yeah, so like I said, the blue trend is showing us what we see in observations, and you can see like on the x-axis, it is saying in observations that the galaxy luminosity is less than what is predicted. So AGN, like I said, it heats up that because of the accretion of the supermassive black hole, it heats up the gas in the galaxy that stops star formation. So if it's stopping star formation, that is going to decrease the galaxy's overall luminosity.
So main point is that it's inhibiting star formation.
Yeah.
Okay.
Mm-hmm.
Thank you.
Yeah. Yeah. Thanks.
Go to the, I think it was the second last slide, just where you had the X-ray contours and the C.
Yeah.
I couldn't help but notice, I know you mentioned that you're going to be looking at position velocity diagrams and other things like that, but it does look like there's a bit of a bulge out in the gas in the direction that the X-rays would be.
That's actually a really good observation.
Do you think that's a real feature of the data, or?
It could be. It very much could be. That's interesting. Yeah. No, our future work is going to be exciting. Yeah, for sure. I didn't notice that, actually. Yeah.
You mentioned at the beginning these are X-ray selected AGN.
Yeah.
Would you be expecting any kind of bias because of that? If you have optical or infrared selected AGN, for example, any kind of differences in your kinematics that are involved in kinematics emission?
Well, all the work I've done on AGN, usually we because of that very intense interaction of the supermassive black hole with its surroundings, is going to emit X-rays. So usually we want it to be X-ray selected because that indicates that there is a relationship with the harsh accretion with its surroundings. So maybe there is potential for doing selection in different wavelengths, but usually I've done it X-ray selected. I've done a previous AGN project and it was also X-ray selected as well. So I don't know. It's a good question.
And there are two ways, right, that you could have no X-rays. One is if there's just no activity in the center.
Yeah, it's a quiescent.
And then a quiescent object, and then how does that change the distribution of luminosities? And then the other way is that there's an awful lot of gas in the middle, and so the X-rays are there, but they're not getting out.
Oh yeah.
Right.
Good point.
And so So it might be worth at least acknowledging those cases in saying, but we're not looking at that in this project.
Okay, yeah, good points. Good point.
Any other last questions before lunch? Seeing none online?
No.
Okay. In that case, we will wrap up this session. We're going to take a lunch break. We're going to be back at 1:40 for the 3 final, very exciting talks. So I hope you'll rejoin us for that. Just a minute. Welcome to the final session of the 31st SAO Astro REU Symposium. And so this session is going to be about black holes, clusters of galaxies, all the seriously far out stuff. And we're going to start off with Jose Pineda, who is from California State University, Long Beach.
That's the full name.
The full name. What do you guys call it?
Cafe Long Beach.
And Jose has been working this summer with Raid Suleiman on a theory project about black holes, which is close to my heart. I, as a grad student, was working on, I was in Cambridge hanging out with all the black hole theory people. And so this is really made me feel nostalgic. So he's going to tell us about energy extraction via magnetic reconnection in a rotating black hole. Take it away, Jose.
Thank you for the introduction, Jonathan. So hi, everyone. My name's Jose. Again, Cal State Long Beach, or California State University Long Beach. And yeah, my project was on the energy extraction via magnetic reconnection in a rotating black hole. So a brief overview of my project. I'm going to first begin with discussing the general theory of relativity. Then I'm going to move on to one of its consequences, black holes. From there, we're going to go into different mechanisms for energy extraction, our focus being magnetic reconnection, and then how to analyze energy extraction via magnetic reconnection using Keplerian angular velocity, the ZAMO frame, and then we can move on to our theoretical setup where we find the energy density, power, and efficiency of the extracted plasma. And then finally, I'll summarize the points of my research. So to begin, 1915, Einstein formally proposed his general theory of relativity, which was a natural expansion to his special theory of relativity. In there, he asserts that gravity is not a force, but rather it's actually the bending and warping of space-time caused by massive objects. Here we have Einstein's field equations. And in there, it basically tells us the relationship between matter and space-time. Matter tells space-time how to bend and warp, while space-time tells matter how to behave and move. And from this equation, what I want you to take note of is the metric tensor, which comes up a lot in our equations, as well as the cosmological constant, which is a huge factor in our research. Reason being is when we have a cosmological constant of 0, we're in flat space-time. When we have a positive cosmological constant, we're in de Sitter space-time, and then a negative cosmological constant, we're in anti-de Sitter space-time. So just keep note of that as we move forward. From here, I want to talk about one of its most prominent consequences being black holes. Black holes are, astrophysical objects that are so dense that nothing can escape its gravitational pull, not even light. And it can be characterized using 3 classical parameters. So that's the spin, mass, and charge of a black hole. Each solution to Einstein's field equations produces a different type of black hole. Our focus is in Kerr black holes, which are non-charged spinning black holes. Kerr black holes have a few key characteristics that we want to take note of. One being its ergosphere that we can see here in gray, which in this diagram is between the outer surface of infinite redshift and the outer event horizon. We take note of that because that is our main region that we see energy extraction as being a viable region to occur. Another important note of Kerr black holes is that it has a frame dragging effect. So not only does it actually bend and warp space-time, but it also drags the frame of space-time, as we can see here, instead of being radially into the black hole, we see that it actually curves space-time as it spins. And this is for black holes of near maximal spin. Now on to mechanisms of energy extraction. The first one was proposed by Penrose in 1969, where a particle of fission occurs in the ergosphere. Initial particle 0 goes into the ergosphere, splits into particle 1 and 2. 2 has an increased energy at the expense of the rotational energy of the black hole. Blanford-Znajek proposed his process of not magnetic reconnection, but his process of energy extraction in 1977, which acquires an accretion disk. and is used for a lot of general relativistic magnetohydrodynamic simulations that we use today. And then magnetic reconnection is a primary candidate that we look into for non-thermal emissions of pulsar wind nebula, gamma ray burst, and active galactic nuclei. And the general idea of how magnetic reconnection occurs is that because of its frame dragging effect, we have anti-parallel magnetic field lines that occur at the equatorial plane. So here we have our Kerr black hole with the axis of rotation along the vertical and our ergosphere in the dotted lines here. And we see that at the equatorial plane within the ergosphere, the magnetic field lines are anti-parallel, which produces a current sheet, eventually destroyed by plasmoid instability, and you get a plasma with negative energy at infinity that falls towards the black hole's event horizon, and then a positive plasma energy density that escapes to infinity. And the point of reconnection is known as the X point, which we'll use that term moving forward. So this huge metric is the way we describe space-time around a rotating black hole using Boyer-Lindquist coordinates as well as natural units, so speed of light and gravitational constant are 1. And then here we also define the spin of the black hole as the angular momentum per unit mass. And so yeah, this is the whole thing that we use with its metric components or metric functions. It's primarily comprised of spin, cosmological constant, and the polar angle, theta. But we can actually do a couple of assumptions or reductions to make the metric a little bit easier to work with. So first is we can look at the space-time that we're working with. So if it's Kerr, again, we can set lambda equal to 1, which gets rid of a lot of these functions here. And if it's non-Kerr or curved space-time, then lambda doesn't equal 0, so we can't do that. But what we can do is, like I'd mentioned before, the magnetic reconnection occurs at the equatorial plane. So we can set that theta equal to pi over 2. And doing that, we get a little nicer of a metric function. The one here is for a flat space-time, and here is curved space-time, and then we only have 2 metric functions to work with or deal with. From there, we can get into the theoretical setup using the Keplerian angular velocity for the bulk plasma at the equatorial plane. So again, for Kerr, we're looking at a lambda of 0, and we can see this function here, or this equation here, has no consideration of lambda. There is no lambda. And then this one does have lambda. So this is for Kerr de Sitter / anti-de Sitter, and this is for Kerr flat space-time. And the plus and minus, plus is co-rotating plasma, where the minus is counter-rotating plasma. And from there, when we plot them, we'll notice the plots are very similar, if not identical. So we have our Keplerian angular velocity by the radius with co-rotating and counter-rotating spins. Or sorry, the spin is unitless, but the plus or minus is the plus or minus that we saw before in the equation. And like I had mentioned before, this is lambda equal to 0, and this is non-zero, but the functions are identical, or sorry, the plots are identical. So we notice that lambda has 0 or negligible effects on the Keplerian angular velocity. From here, I would like to introduce the ZAMO frame. This is the Zero Angular Momentum Observer frame. And we use this frame because within this frame, space-time is locally flat. So instead of using Boyer-Lindquist coordinates, we can actually use Minkowskian coordinates using a set of transformations that go way over my head. But if you're really into math, that's your thing. But we use the ZAMO frame to find the Keplerian velocity, which is Vk, and it's a function of the Keplerian angular velocity, as well as the azimuthal component of the metric here. And so you'll notice that it should vary as we use de Sitter, anti-de Sitter versus flat spacetime. And we do notice a large difference. These aren't identical plots even in the x and y axis, but here we have Vk as a function of the radius. And we'll notice we vary spin, and we'll notice that Vk approaches 0 as r increases. But here instead we have Vk as a function of lambda. And we'll notice, and we vary r here, but instead we keep spin constant. And we'll notice that around lambda equal to -4, all of the Keplerian velocity approaches 0, which is an interesting characteristic we found. Question?
What does it mean to have a speed greater than 1? Is it greater than the speed of light?
The spin?
The
VK on the right.
The VK. I'm not sure about the physical properties of VK. I don't think it means greater than speed of light, but yeah, I'm not sure. But to move forward, another component that we look at for the energy density of the extracted plasma is the energy momentum tensor of the plasma. And to find that, we first start with a perfect fluid approximation with non-zero pressure given here. And we also want to include the electromagnetic component, which is this with the square of the electric field here and the square of the magnetic field given here. I guess expanding that, you'll find this is our electromagnetic component, so we can combine our electromagnetic component with the fluid component, resulting in a total energy momentum tensor of this that we use for the energy at infinity density. So that general equation for energy at infinity density is given here. Plugging in our energy momentum tensor, we get this equation, which is comprised of the lapse function, total energy density, the shift vector, and the azimuthal component of the momentum density. From that, we get the best equation of my research, which is this guy, which is made up of a lot of stuff. But really, it's actually kind of nice in that it's only comprised of 4 to 5 different parameters. So the black hole spin, distance of the X point, plasma magnetization, and orientation angle. And if we want to consider a non-zero lambda, then we'll consider lambda. But from here on out, we just look at curved black holes. So we have lambda equal to 0. And then quickly to define the orientation angle, that's the angle away from the equatorial plane. So luckily, we don't have to deal with that massive equation too much because there are some approximations we can use. So some of the, for the conditions, assuming conditions for sizable energy extraction given up here, these actually reduce to these equations here where this is the energy density of infinity of the plasma that escapes to infinity, which actually reduces down even further to the square root of 3 times the plasma magnetization. And we can see how well that approximation is here. And then here we have the energy density of the plasma that falls into the black hole event horizon, given with this equation here, which is the negative square root of the plasma magnetization over 3, which is even better approximation than the energy density that escapes to infinity. So using those approximations, we can find the power of the extracted plasma, which is largely dependent on the plasma that falls towards the black hole. And here we have AN as the cross-sectional area, and then UN is the collisionless regime of the order of 10 to the minus 1. So plotting the power extracted from the plasma, we find that the power extracted as a function of the R. For this first graph, we leave plasma magnetization constant with a near maximal spin and orientation angles varying. And then for the second one, we keep orientation angle constant, near maximal spin still, but this time we change the plasma magnetization. And you'll notice in both graphs that around 1.2, we see the height of each parameter, I guess, is at 1.2. So the most power extracted is around 1.2 from the event horizon. And then you'll notice that the closer we are to the equatorial plane, the more power extraction we see. And then the higher plasma magnetization, the more power extraction we see as well. Lastly, we have this nice little equation that we use to find the efficiency of the curved black holes. And keep in mind that energy extraction only occurs when efficiency is greater than 1. And here we have the spin from 0.9 to 1, so all very fast spins. And as we vary the spin from 0.9 to 1, we'll notice that the efficiency, it becomes less efficient, the energy extracted. So as we get closer to 0.9, anything lower than that, we basically don't get any energy extracted. As well as you'll see that as we decrease the spin, the maximal height of efficiency is farther away from the outer event horizon. All right, so in the interest of time, I'm just going to go ahead and leave my summary slides up, but that was my talk.
Thank you, Jose. Questions?
So I have a question and a possible follow-up depending on your answer. So how do you define the plasma magnetization in this scenario?
So plasma magnetization, I didn't look too much into that. I just kind of use it as a parameter that we change Are you talking about specifically like what it is?
Yeah, so what plasma properties go into that to actually make that value? So, I stare at the sun, so I have a particular, so usually the people who look at the sun and people who look elsewhere have different definitions for things in terms of plasma physics. So usually we consider it the collisionality for a particular charged species over its like Larmor radius. So it's like how much is the magnetic field affected as opposed to collisions with other things.
I see.
So is it something like that? Do you know?
I'm honestly not too sure. I was under the assumption with my undergraduate, level of understanding that it was just the magnetic dipole per, volume of the plasma. But that's not from literature. That's just from like
you're kind of taking a
undergraduate
material
classes.
definition to it. Okay.
But
is that right, Brady?
Yeah, in my courses, so I will try to do my best. We look at it from the magnetic field effect in general. We want to plan even to plan all kinds of connections on it to see how much that will have an effect in the energy we extract. So we are not looking at it from the solar perspective, where there are more granular interactions within the plasma.
So you're almost treating it like a material solid in a way. So
not totally solid, but yes. But the idea is we want to just emphasize the magnetic field and at the same time try to understand how much would that value. That's why we didn't give it a number. We didn't say, okay, it's equal to that. So it's still out there. For us, we want to know how much extraction we will get as a function.
okay, yeah, okay, I can see what the definition is. I'll let somebody else ask a question, but I have another. So.
Other questions? I have a question. So when you were talking about how lambda didn't make much of a difference in one of the early graphs, the value of lambda you were using was lambda m squared is 0.01.
Yes.
And I'm wondering what the valid ranges of lambda are and how you picked that one.
Yeah. So this is based off of literature that we're working off of, where we have lambda m squared equals to 0.01. But I was considering, would that change whether we changed our value of lambda? So I would like to kind of delve into that in the future.
See, that seems like, okay, somehow that's a small value.
Yeah.
Maybe if lambda is of order m or something like that.
Or to explore this is to actually have lambda as a function of R and then have the efficiency
as a function of R.
As a function of lambda as well.
Yeah. Okay, that makes sense. Yeah. Thank you. Do you want to ask your other question?
Yeah, so you showed early on in the talk that you get these current sheets that form.
Yeah.
And you say they dissipate from the plasmoid instability. So imagine this is a very I'm going straight to plasma. This is most solar physics question. So you have the plasmoid instability. So this is going to be a very highly ionized plasma, I imagine it. So definitely these are energies bigger than what we see in the sun. So I'm wondering what the time scales are for these plasmoids to actually become unstable and dissipate out their energy, because after a while you're going to have issues sustaining your magnetic field.
Yeah.
So I was wondering, do you have an idea of kind of how quickly this process happens?
Yeah, I think it's very, into the thick of theoretical, so we just kind of assume, okay, this is something that happens, and then from there we're going to see how efficient it can be. But of course you saw there's a lot of assumptions that we made. So in that, we don't really look at, there's something that someone else brought up to me, is that can black holes even have a magnetic field that looks exactly like this, right? Is this a viable kind of assumption that we make? So that's just something we didn't really look at, was how long it would take, but I assume it's much faster than magnetic reconnection you would see on the sun.
Okay, yeah, that'll be interesting, because now you're going to have to ask, the source of the magnetic field, is it coming from the actual rotation of the black hole? Is it coming from the actual plasma in the accretion disk? So, because I can see time scales where if that current dissipates too quickly, because it's going into plasmoids and it's just kind of circling around, you're going to have all these very local perturbations to the magnetic field, but you're going to shut off kind of the overall dynamo that's kind of holding things together. So it would be interesting to see kind of how that time scale compares to maybe like AGN, you know, going through history or something like that. So I'm trying my best to be.
If you're flowing in, if you're accreting stuff flowing in, and you're bringing magnetic field in from outside and squeezing it as it gets close.
Yeah, because the magnetic field is going to be locked in, because I'm assuming everything's going to be fully ionized. So, but you still need that current sheet to sustain things. So.
Okay. All right. Thank you again, Jose. All right. Crystalline is up.
We have 2 laptops in play.
Well, while we're getting set up, I'll mention that we are currently applying for renewal of the REU grant. Assuming that we get that, we will be soliciting projects from CFA scientists in the new year. So it's not too early to start thinking about, do you want to be an advisor next year, and what projects might you come up with?
During
We'll take time.
And then lastly, make special. Hello? Wait. I'm really loud, so I want to make sure that I cut into your ears in the next 13 minutes. Hello?
Yeah.
Okay.
That's good.
And then the slide.
So our next speaker is Crystalline Larkin from Brown University, not so far away. And Crystalline has been working with Paula Dominguez-Fernandez and Federico Fraschetti on shock waves in the turbulent magnetized intercluster medium. Crystalline, let's hear what you have to say.
Exciting. Okay. Good afternoon. My name is Crystalline Larkin, and today I will be talking about radio relics and magnetic field amplification in galaxy clusters, particularly in what they reveal about the interaction between shocks and turbulence processes. Before I go on, I first want to go over the outline for today's talk. First, I'm going to cover the evidence of diffuse radio emission. What are radio relics? Why are they important to study? What do their characterizations imply? And lastly, what can we take away from this summer? So the cosmic web shows the distribution of galaxies. Where these galaxies tend to clump up are known as galaxy clusters. They are the largest objects in the universe held together by gravity, where their typical masses range from 10 to the 14 to 10 to the 15 solar masses. Of that mass, 2% of that is the actual galaxies themselves, 85% is dark matter, and lastly, the 13% is the intracluster medium. Hello? Okay. So this 13% is particularly really important in the context of studying radio relics because that is where we can detect them. So the intracluster medium, or the ICM, is a hot, diffuse, weakly collisional ionized plasma that fills galaxy clusters. So in between these green galaxies that we see here in, in the green, we have the ICM. And we can break the ICM down into 2 main parts. The first is the thermal component, which we can observe using X-ray observations. And the second component is the non-thermal part, which we can observe using radio observations that reveal the presence of cosmic rays, magnetic fields, and turbulence. So as these galaxy clusters form, we have these two clumps that we see here in X-ray merged together. And as a result, the shocks propagate through the ICM. And in coexistence with these shocks, we can find this diffuse radio emission here that we call relics. So diffuse radio emission typically falls under megaparsec scales. And due to their large sizes, we find a variation in their general shape and location. So we typically classify them into two main categories. The first are radio halos, which are unpolarized sources typically found in the center with rounder morphologies. So here I have a picture of Abel 2744 with a nice halo smack dab in the middle of that cluster. On the other hand, we have radio relics or radio shocks, which are highly polarized sources typically found in the galaxy cluster's outskirts with elongated shapes. So I have a picture here of a famous radio relic called the toothbrush cluster, particularly where we can see its figurative handle jet out. We can see that elongation characteristic here, but also we can see it also in this picture of Abel 2744. So that reveals that in addition to this halo that this cluster has, it also has a radio relic. Based off of these two images of these radio relics, we can see that radio relics are not uniform, but rather they have substructure and different morphology. Radio observations essentially revealed that radio relics can generally vary in terms of their shape and size, but also as this high close-up, this high resolution close-up picture of this toothbrush reveals, is that radio relics can also have unique substructure features. So we can see, for example, the bristles kind of jet out of that toothbrush, and unique characteristics like this emphasize the importance of studying radio relics in terms of specifically for their formation to emphasize, with a particular emphasis of the different pre-shock conditions that kind of differentiate what's a sausage radio relic from a toothbrush, for example. So the way that we currently theorize is exactly happening at the shock front to allow us to explain radio relics is called the DSA process, or long-term diffuse shock acceleration, DSA. So the DSA process essentially first requires that particles first meet the injection momentum to first enter the shock front. Once it's able to enter the shock front, then these particles can effectively scatter. So each time that it crosses upstream and downstream, crossing the shock front, the particles gain energy each time it crosses the shock, allowing the particle to further jet out, enabling this process to become diffusive. Particularly, eventually, DSA predicts that whenever these electrons gain enough energy, cosmic ray energy, we can use this relationship here that's based off of the shock's Mach number, which is essentially just a quantity that we use to define the shock strength, where Mach is essentially the ratio of the shock's velocity to the speed of sound. And we use this quantity to kind of determine the spectrum of electrons that we get as a result. So our overall project motivation is to use simulations to replicate relics and their substructure under realistic turbulent ICM conditions. So this is a very ambitious goal. So we broke down this project motivation into two main goals. The first is what we focused on this summer, where we focused on replicating the MHD fluid under DSA theory. And the second goal is to model synchrotron emission, where we test under two different electron population types, which I can get further into later in this presentation. But nonetheless, this overall project aims to gain a better understanding of what is exactly happening at the galaxy cluster periphery, specifically in terms of the interactions between the magnetic fields, where the DSA comes into place, possibly explaining the origin of these cosmic electrons, and more accurately, just gaining a better picture of what is exactly happening to explain the diffuse radio emission that we observe. So over here, this is a spoiler alert of what is to come later in the project, but what we specifically focused on is this visualization of the MHD fluid simulations. So we aim to build a parameter space for this type of fluid to be accurate. So we use a shock tube setup where we tested how 4 different shock strengths of Mach number 2, 2.5, 3, and 3.5, how did they face the influence under 3 different initial conditions that essentially varied based off of how much the turbulent conditions were composed of solenoidal and compressive vector fields. So that's a visualization, a video of the shock propagating. But if we wanted to really compare how these different shock strengths look under the same forcing amplitude, I show a projection of the magnetic field from the z-axis to kind of compare how these different shocks would look under 100% solenoidal conditions. As you can see, in order for the shock to propagate to the same position in the box, it's a little bit more compressed, but it's the same box, I promise. But nonetheless, we can see that stronger shocks propagate the shock on faster time scales. But in addition to that, where the shock is, you can't really see that with the resolution of this, but the shock front is at 1.7, and if we were to compare a shock that is Mach number 2 to 3.5, we can see that the definition of the shock front becomes more defined. So from Mach number 2, we can see that the fluctuations of that shock front are less for 3.5. But overall, we can see that in addition to making the shock front substructure more defined, that there is a general amplification for stronger shocks of the magnetic field. So this general pattern that we see where stronger shocks not only propagate on faster time scales, but also magnify the magnetic field to higher levels, we can kind of see that evolution over time here with these time evolution plots, where we wanted to compare how did that general relationship where stronger shocks amplify compare over different forcing amplitudes. So as you can clearly see, the forcing amplitude doesn't change significantly, and this is specifically looking at the downstream region 100 kiloparsecs behind the shock. So in addition to taking a look at the magnetic field, we also took a look at the Mach number distribution. So basically the distribution of the Mach number that the shock detector finds as the shock propagates through over time. This is an example of one of our cases where we show that distribution. However, for all of our runs, we see that for stronger shocks, there's a broadening of this distribution. But in addition to that, we can see that for all of our runs, that the higher the forcing amplitude, it also has the pattern of broadening that Mach number distribution. So we kind of summarized that broadening here, where we plotted the standard deviation, where we can see that for shocks Mach number 2, 2.5, 3, and 3.5, that for each case, the forcing amplitude for higher amplitudes generates higher standard deviations. This is particularly really important in the context of relating it back to DSA theory, as if we remember when I was talking about the electron spectrum, it uniquely relates back to the Mach number. So basically, this plot allows us to determine that if we can directly observe the fluctuations, we can differentiate using a relationship like this to differentiate the initial conditions. Okay. So overall, that as this implication kind of shows us is that we need to study more of the shock properties. And so we plan to further investigate other properties such as the shock obliquity, the magnetic field and velocity power spectrum, and the solenoidal and compressive components, and then further link that back to how do the synchrotron emission variations vary for these two different types of electron populations. So that concludes my talk. Thank you. I need water.
All right. Thank you, Crystalline. Questions for Crystalline?
So the future kind of so the future
I
MHD
could rely on you.
So the future MHD simulations that you showed, and some of the ones that have been done prior. So I'm just wondering kind of what the setup is for that. Is it just going to be kind of a single fluid going into a shock? Do you have both electrons and ions, or are you just kind of taking it as just one single fluid?
So we basically wanted to replicate. So there are many different. It's convoluted with different conditions.
It's hard.
So, huh?
It's hard playing God.
Yeah. Is there one single fluid? So there is one single fluid where we just basically replicate based off of the MHD jump conditions, where on the left is it's determined by the MHD jump condition. So essentially, it is one fluid. Yeah. And then we just see how, based off of the theoretical descriptions in terms of how it relates back to the gas plasma on the other side of that shock front in terms of the simulation. So that's why we kind of see that here.
Yeah, that's a really cool simulation. So, but yeah, does that include magnetic field information in there?
Yes.
Okay.
Oh, this is the projection of the magnetic field.
Oh, that is the magnetic field. Yeah. Okay, I thought that was plasma density. Okay, that makes a lot more sense now.
Yeah.
That's why it's true in utter chaos. Perfect.
Are there any questions online?
Cheers.
Can you go back to the, you were originally showing the non-thermal and the thermal. There was a map, an observational map. I just wanted to.
Oh, this.
That one. Yes, thank you. I just wanted to be okay. No, you did label it.
Yeah, sorry. It's
I didn't see that. Yeah, okay, so the
contrast.
so the thermal is the from the X-ray data, and the non-thermal is from the radio data.
Yeah, it's the same.
Right. Got it. Okay. I just missed that earlier. Any more questions?
Lovely.
Okay, I guess you explained it pretty well. So we're going to move on to our very final talk. Last but very much not least.
Thank you.
Last but not least.
Yeah, exactly. So Anika Kumwembe is an undergraduate at St. Mary's College in Maryland. And has been working this summer with Claire Lamon and Dan Eisenstein on the DESI survey and catalogs in the DESI survey. So Anika, let's hear what you have to say.
Is this good?
Yeah, I can.
Is this
Can you
good?
hear people?
Yeah? Okay. All right, hello, my name is Alexis Anika Kumwembe, and I'm here to talk to you guys about understanding the large-scale structure of the universe with enhanced multiplet catalogs. So intrinsic alignment and the cosmic web are two very important ideas when it comes to our project. So the cosmic web can tell us a lot about dark matter and dark energy, and it also contributes to the shape and the structure of the universe. And most importantly, it also traces around dark matter. So instead of using galaxy positions to map out the universe, we can also use orientation. And this is where intrinsic alignment comes in. So this involves the correlation between galaxy shapes, spins, and the cosmic web itself. And another important idea to take account for is that galaxies tend to point towards regions of higher density. So we're going to be using information from DESI, and DESI's main job is basically to make a 3D map of the nearby universe, and it currently has the largest 3D map. And then, does this work? Yes. And then, so here's just a piece of that map that they're currently making. So, what are multiplets? So, multiplets are small groups of galaxies, and they're very useful for us to find alignments. So, there's two main parts of multiplets. So basically the first part is the center galaxy. So the center galaxy is found in the spectra catalog, and it's important for us to know the distance of the multiplet. So another thing is the neighbor galaxies, which is the second part of the multiplets. Basically, these galaxies are found in proximity to the center galaxies, and limits can be applied to these neighbor galaxies in order to do more research on what we're doing. So over here, we basically have a plot of one of the multiplets that we found. The y-axis is declination, and then the x-axis is right ascension. And then we can see here that the blue dots are the neighbor galaxies, and then the yellow dot over here is the center galaxy. So we can use multiplet alignments to view tidal signal. So we can get alignments from multiplets instead of individual galaxies, and this helps us understand the large-scale structure of the universe. And the reason why we want to do this is just because it's a lot more complicated to get the orientation of individual different galaxies. And this is because there are many systematic errors with imaging. And then also, along with that, some galaxies don't even have a singular alignment, so we'd be losing a lot of information. So having alignments of groups of galaxies is a lot more reasonable. So in the lower right over here, this is basically a depiction of how we're finding the alignment. So basically, we take the average orientation of the different galaxies in the multiplet, and that's how we get the alignment. And then the transverse separation R is the distance between the center galaxy and the tracer. So multiplet alignment tidal signal and tidal signal. So from the multiplet alignment, we can also get tidal signal. So the large-scale structure of the universe creates a tidal field through gravity, and it also tells us how these objects are correlated gravitationally. So over here, we have a graph, and in general, what I want you guys to understand from this graph is that the closer a multiplet is to a tracer, the higher its signal. So basically, this is on a logarithmic scale. So this is the projected separation R that I was just talking about between the center galaxy and the tracer. And then this is just the signal that we get from those multiplets. So as we can see here, in general, the closer the multiplet is, the less the separation is, the higher the signal. So what are catalogs and why do we use them? So catalogs basically show us coordinates of galaxies on the plane of the sky. And this can help us by organizing information into arrays, which helps us easier use this in code. So basically it helps us with everything that we use in coding, and then it also makes it easy for us to actually plot information in graphs, so such as like histograms, scatter plots, and other such things. So there are two main catalogs that we use. The first one being the imaging catalog. So this only uses imaging. It doesn't give a specific distance, and also DESI selects most of its galaxies from this imaging survey. The second catalog is the spectra catalog, which does have distance. It has spectrum, so we can actually tell the distance in space. So on the upper right over here, we see the full imaging catalog. And then on the lower right, we see the spectra catalog. And then I want you guys to sort of see how here in the spectra catalog, it's a bit more spotty than the imaging catalog, which has more of a uniform look to it. It has a lot more information. So what's the issue? Well, the spectra catalog has less objects than the imaging catalog, as we had just seen before. So that means that not all center galaxies in the spectra catalog will have neighbors. So if we don't have neighbor galaxies for our center galaxies, we can't get multiplets. If we can't get multiplets, then we can't find the orientation or intrinsic alignment. And if we can't find that, then we can't get the tidal signal. And if we can't get the tidal signal, well, we won't be able to understand the large-scale structure of the universe. So in order to fix this issue, why don't we supplement it using the imaging catalog? So we can use imaging to help us make multiplets and view tidal signal. And in general, with the imaging catalog, the galaxies are on the plane of the sky. And because the multiplet is actually projected, we can just use angular positions. So in this case, the lonely center galaxies from the spectra catalog can get neighbor galaxies from the imaging catalog. And then the additional multiplets from the imaging catalog can help us further our understanding of the large-scale structure. So over here is basically actually an image of one of the multiplets that we found. And you can see right in the middle over here, we have this sort of dim red galaxy, which is actually our center galaxy, our spectra galaxy from the spectra catalog, yeah. And then we can see that in the rest of this image that we can assume that there are many more objects that are included in the multiplet in this image. So when it comes to actually making our multiplets, LRGs, or luminous red galaxies, are the best or strongest tracers. And so they are large elliptical galaxies that lack new star formation, and they are located in clusters, which is really useful for when we're making multiplets. So the positioning is also correlated with the cosmic web. So over here on the right, we have sort of like a slice of the cosmic web. And we can see here that the further the redshift, the redder the galaxies, and all of these red dots over here are the LRGs that we really want to take into account when making our multiplets. So that's what's going to be really useful for our project. And then in general, when it comes to our neighbor galaxies, we have two main limits. So the first limit that I'm going to talk about is distance. So for this project, we had multiple different distances, but I'm going to be focusing mostly on the first distance that we chose, which was 0.6 arc minutes. So basically, this distance has a couple of advantages. It helps us actually get galaxies that are gravitationally connected to our center galaxy, and then it also helps us sort of block out any other random objects that may not be as useful for our multiplets. So it gets rid of all the interlopers, anyone that just really isn't important for what we're looking for. And then this depiction on the right over here is just relating to the angle and then the distance between the galaxies. Our second limit is basically limiting by color. So for this project, we chose specifically the R-W1 color. And this is due to the fact that it has a strong correlation with redshift. And then for cosmologists, redshift tells us about the distance of a galaxy. So basically, the redder the galaxy, the further away it is. And in this case, also, color difference tells us the distance to certain galaxies, which is also very helpful for the information that we need. So in general, when it comes to our results, we had some really good results. We can see here, this is the original red line that we looked at in one of the first slides. And this is with just using the information in multiplets and galaxies, neighbor galaxies, from the spectra catalog. And then here, we can see that the blue dashed line is what we get from the imaging catalog. And so this is actually really great for us because we're seeing here that there is a similar shape and a similar signal to noise. So this is very great for our research because it's showing us that we're actually making really good measurements on the same objects that we would from the spectra catalog, and that the objects from the imaging catalog and the measurements from the imaging catalog are on par with the measurements just using the spectra catalog, which is great for us. And then over here on this graph, I'm basically just showing different measurements. And for the first two, we have the enhanced multiplets with just the distance cut. And then we have it also with the color cut. So we can see certain differences here, which are very interesting. And then for the last one, for the enhanced multiplets, this is the one with a different distance, which is 1.8 arc minutes instead of 0.6 arc minutes. So looking into those differences can be really interesting and probably help us further determine which measurements are the best and what can help us along the way. So in general, this shows that we can use imaging to enhance the spectrum multiplets, and it's also just the main idea is that we got tidal signal from using the imaging catalog, which is really great for us. Thank you. Questions?
Do you have a sense of how many extra multiplets you're finding when you include like the imaging catalog now?
How many extra ones?
Yeah.
Okay, I'm not too sure about that, but I know that when we do find other multiplets, when we make most of the distance cuts and the color cuts, we do retain at least like 70% of those multiplets, which is really good. Yeah.
So thank you for a great talk.
Thank you.
Would it be correct to infer, since W1 is Y, is band 1, that's an all-sky survey, and I think R is probably pan-stars, would it be correct to infer that this technique, now that you've benchmarked it against DESI, you could expand it to the entire footprint of pan-stars, the whole, I don't know what fraction of the sky that is, but it must be big chunk of the sky.
So I think the R color correlates to something with DESI specifically, but in general, I think we could use this basically for all objects in the sky. I mean, that would make us, I guess we would be using different distances and then maybe not make color cuts in order to actually take into account many other different stars and not just specific ones for specific projects or research.
Yeah, Christine.
Who are the people?
Oh, this is a small chunk of the DESI collaboration. Yeah. Yeah, took it right from the webpage.
So when you were doing the imaging cuts, but you're still using spectra as the central galaxy, is that right? Or
Yes.
Yeah.
So we're basically taking the central galaxies that we're basically still taking the central galaxies from the spectra catalog,
Right.
but
So
we're
I think
using.
that's the difference from what you were saying. Is does pan-stars have? You'd have to use photometric redshifts, I guess, or.
Well, she's invented a color. And
Right.
That could,
So you could use the photometric redshift, yeah. Okay, so maybe you could, yeah.
All right.
So I'm trying to understand, that color difference, is that comparing to that central galaxy, or is that just in general? I thought, if my understanding was correct, that coloring difference was comparing to the measured color of the central galaxy.
Yes.
The galaxy you have spectra for.
Yes.
Because this is a way to try and avoid having lensed galaxies in your sample, in your multiplet, right?
Yes, that's correct. Yeah.
Okay, thank you.
You do need spectra of the central galaxy when correlating with stressors.
Yeah, that's what I was, yeah.
For the distance, yeah.
From risk of relapsing and contaminating this.
Yeah, okay, that makes sense. All right, any last question for Anika? In that case, let's thank not only Anika again, but all the speakers today who did just a great job today. Throughout the summer, I'm so proud of you all.
Thank you.
This brings this year's REU program essentially to a close. We'll have a wrap up for the team tomorrow. So once again, well done everyone. Thank you for participating. A special thank you to the advisors, without whom we could not do this program, obviously, and you've just been fantastic. Thank you for all the work that you put in.
let's thank Jonathan for running the program.
And there's still some food at the back.